Welcome back, Night Traveller. Tonight, we're drifting into the quantum realm, that strange, beautiful layer of reality where particles dance between existence and possibility, where the very act of looking changes what you see. If you're finding comfort in these late-night explorations, consider subscribing to join us on future journeys through science and wonder. Now, let's begin. Maybe you've heard the term quantum physics before, whispered in science fiction, tossed around in documentaries, used to describe anything mysterious or confusing. But what is it really? At its heart, quantum physics is simply the study of how matter and energy behave at the smallest scales imaginable. We're talking about atoms, those tiny building blocks of everything around you. We're talking about electrons, even tinier still, orbiting those atoms. We're talking about photons, particles of light that have no mass at all, yet somehow carry the energy that lets you see these words. At this scale, so small that millions of atoms could dance on the head of a pin, the universe stops following the rules you learned growing up. Objects don't have definite positions until you look at them. Particles can be in two places at once. Things can pass through walls they shouldn't be able to penetrate. It's a realm where common sense takes a vacation, and reality becomes something stranger, more fluid, more uncertain. And yet, for all its strangeness, quantum physics is perhaps the most successful scientific theory ever created. Every prediction it makes, no matter how bizarre, has been confirmed by experiments. It's the foundation of chemistry, the backbone of modern technology, yes, the key to understanding why matter exists at all. So as we drift through these quantum facts tonight, remember, this isn't science fiction. This is the actual architecture of reality, operating silently beneath everything you've ever touched, seen, or thought about. Strange? Absolutely. But also, in its own way, deeply, quietly true. The word quantum itself is worth lingering on for a moment. It comes from the Latin quantus, meaning how much. A question about quantity, about measurement. And that's fitting, because quantum physics was born in 1900 when a German physicist named Max Planck asked a simple question about how hot objects glow. He was studying black body radiation, the light emitted by heated objects, and the equations everyone was using kept giving nonsensical answers. So Planck tried something radical. What if? No, he wondered, energy doesn't flow smoothly like water from a tap. What if it comes in tiny, discrete packets, little bundles that you can't divide any further? He called these packets quanta, the plural of quantum. And when he did the math with this strange assumption, everything suddenly worked. The equations matched reality perfectly. At first, Planck himself didn't quite believe it. He thought it was just a mathematical trick, a convenient fiction that happened to give the right answers. But it wasn't a trick. Energy really does come in packets at the quantum scale. Light arrives in photons, matter vibrates in discrete steps, even the spinning of electrons comes in specific quantized amounts. It's a bit like discovering that water, which seems so smooth and continuous when you pour it, is actually made of individual molecules. Except in this case, the discovery was even more fundamental. It revealed that energy itself, the most basic currency of the universe, is granular, chunky, countable. There's a smallest possible amount of energy for any given situation, and you can't have less than that. The universe, it turns out, doesn't do infinitely smooth. It does discrete. It does quantum. Here's where things start to get genuinely strange. Light. That familiar phenomenon streaming through your window right now or glowing softly from your screen. behaves as both a wave and a particle, depending on how you look at it. Not sometimes a wave and sometimes a particle, switching back and forth, not approximately one or the other, actually truly both, simultaneously. When you send light through a small slit, it spreads out in ripples, creating interference patterns just like water waves do. It bends around corners, it adds and cancels with itself in ways that only waves can do. But when you try to detect where that light actually is, you find it arriving in discrete little packets, photons, hitting your detector one at a time like tiny bullets. Each photon has a specific energy, a specific momentum. It's countable, particle-like, definite. This dual nature baffled the greatest minds in physics for decades. How can something be both? It feels like saying an object is both a sphere and a cube, both red and blue, both here and there. Our brains struggle with it because we evolved to understand medium-sized objects at medium speeds, things we can touch and throw and eat. We didn't evolve to have intuitions about photons, and yet this is how light is. Not because we're confused or our instruments are bad, but because reality at the quantum level genuinely doesn't divide cleanly into waves and particles. Those are human categories, invented to describe the macroscopic world. Down in the quantum realm, things are what they are, something richer and stranger than our vocabulary can capture. Perhaps light is teaching us that nature doesn't care about fitting into the boxes we've built for her. Perhaps the lesson is that reality is under no obligation to make sense to creatures who only recently climbed down from the trees. When you learned about atoms in school, you probably saw a familiar picture, a nucleus at the center, with electrons orbiting around it like planets around a sun, neat, tidy, mechanical. It's a comforting image. The solar system in miniature, following predictable paths through space. But that picture is wrong, beautifully, productively wrong, useful for learning, but not how things actually are. Electrons don't orbit, they don't follow paths at all. Instead, they exist in what physicists call probability clouds, regions where they're likely to be found if you go looking for them. Before you measure an electron's position, it genuinely doesn't have one specific location. It's smeared out, existing as a haze of possibility throughout the cloud. Imagine trying to point to where a musical note exists in a room. Is it here? There. The note fills the space. It doesn't have a location in the way a chair does. Electrons are a bit like that, except even stranger. Because when you do finally measure where an electron is, you find it in one specific spot. The cloud of probability collapses into a single point, and then, if you stop looking, it spreads back out into a cloud again. This isn't because electrons are moving too fast to track, or because our instruments aren't precise enough. It's because, before measurement, the electron literally doesn't have a definite position. Asking where exactly is this electron is like asking, what's the exact temperature of a single atom? The question itself is based on a misunderstanding. Position, in the quantum world, isn't something particles have. It's something they acquire when interacting with other things. Until that interaction happens, there's only probability, only potential, only the soft mathematical mist of what might be. Quantum mechanics wasn't discovered by one person having one brilliant insight. It emerged gradually. It's just over several decades in the early 20th century, built by some of the most remarkable minds in the history of science. There was Niels Bohr in Copenhagen, proposing that electrons occupy specific energy levels in atoms. Werner Heisenberg in Germany, developing a mathematics of uncertainty. Erwin Schrödinger in Austria, writing an equation that describes how quantum states evolve, Max Born interpreting Schrödinger's waves as probabilities, Louis de Broglie suggesting that particles could also be waves, and yes, Albert Einstein, who helped birth quantum theory by explaining the photoelectric effect, showing that light comes in packets called photons. But here's the beautiful irony. Einstein never accepted the full implications of quantum mechanics. He contributed to its foundation, won a Nobel Prize for quantum work, and then spent the rest of his life arguing that the theory must be incomplete. God does not play dice with the universe, he famously said, rejecting the idea that randomness could be fundamental to reality. Einstein believed there must be hidden variables, some deeper layer of reality that determined quantum outcomes in a predictable way. He thought quantum mechanics was probably correct as far as it went, but that it was describing our ignorance rather than true randomness. He wanted a clockwork universe, deterministic and knowable, even if the clockwork was hidden from view. He was wrong. Experiments have since shown that the randomness is real, not just apparent. The dice rolls are fundamental, but Einstein's dissent was valuable anyway. His challenges forced other physicists to sharpen their arguments, to prove what they claimed, and to build the experimental tests that confirmed quantum mechanics beyond any reasonable doubt. Sometimes the greatest contribution a genius can make is to be brilliantly, productively wrong, pushing everyone else to be more certain of what's right. And even in his wrongness, Einstein's voice echoes through quantum physics, reminding us to question, to doubt, to demand that nature show her cards before we believe anything too strange. In 1927, Werner Heisenberg discovered something that would forever change how we think about knowledge itself. He found that there are pairs of properties, like position and momentum, that cannot both be known precisely at the same time. The more accurately you measure where a particle is, the less you can know about how fast it's moving. The more precisely you pin down its momentum, the fuzzier its location becomes. This isn't a technical limitation. It's not about needing better microscopes or more sensitive detectors. It's woven into the fabric of reality itself. There is no hidden truth waiting to be uncovered, no secret Weijian momentum that exist but remain hidden from our instruments. The universe itself doesn't keep track of both simultaneously. It's as if reality has a budget for specificity, and spending it on position means having less left over for momentum. Think about it this way. To measure where something is, you need to interact with it, maybe bounce a photon off it. But that photon carries momentum, and when it hits the particle you're measuring, it gives the particle a little kick. You've changed what you were trying to measure. The gentler you make your measurement photon, to avoid kicking too hard, the less precise your position measurement becomes. The more precise you try to be about position, the harder you have to kick, and the more you disturb the momentum. But even this explanation makes it sound like a measurement problem, and it's deeper than that. Heisenberg's uncertainty principle reveals something profound. The universe doesn't contain particles with definite positions and momentums that we simply can't access. Instead, particles genuinely don't possess both properties simultaneously. Before measurement, they exist in a state where position and momentum are both fuzzy, both uncertain, both undefined. It's enough to make you wonder what existence even means. If things don't have definite properties until measured, in what sense do they exist beforehand? Perhaps existence is more verb than noun, something particles do rather than something they are. Perhaps the universe is less like a collection of objects and more like an ongoing conversation between possibilities, with measurement being the moment when possibility crystallizes into actuality. Or perhaps we're using the wrong words entirely, and reality is something our language simply wasn't built to capture. Imagine flipping a coin. While it's in the air, spinning, you might say it's neither heads nor tails yet, it's undecided. But of course, at any given instant, one face is pointing up and one is pointing down. The coin has a definite state. You just don't know what it is until it lands. Quantum superposition is nothing like that. A quantum particle in superposition isn't secretly one thing or another that you simply haven't looked at yet. It's genuinely both things, or all things simultaneously. An electron can be spinning clockwise and counterclockwise at the same time. A photon can be polarized vertically and horizontally at once. A particle can, in a very real sense, be in two different places simultaneously. This isn't metaphorical, it's not poetic license. When physicists say a particle is in a superposition of states, they mean that the particle literally doesn't have a definite state. It exists as a combination, a mathematical sum, of multiple possibilities. And here's the strange part. Those different possibilities can interfere with each other the way waves do. A particle in two places at once can interfere with itself, creating patterns that would be impossible if it were really only in one place. But the moment you observe the particle, the moment you measure which state it's in, the superposition collapses. All the possibilities except one vanish, and you find the particle in a single definite state. It's as if the universe was holding multiple options open, keeping them all in play, and your observation forced it to choose one. Why does observation have this effect? Nobody knows. It's called the measurement problem, and it remains one of the deepest mysteries in quantum mechanics. Some physicists think consciousness might play a role, that minds somehow collapse quantum states. Others think any interaction with a large object counts as measurement, no consciousness required. Still others believe the other possibilities don't vanish at all. Yeah, but split off into parallel universes where those outcomes happened instead. The mathematics of superposition is crystal clear and perfectly predictive. But what it means, what's actually happening when a particle exists in multiple states at once, remains beautifully, maddeningly unclear. Maybe the universe is content with that uncertainty. Maybe reality doesn't need to make sense to observers. Maybe it's enough that it simply is, in all its strange multiplicity, until the moment we force it to declare itself. You've probably heard of this one, the cat in a box that's somehow both alive and dead at the same time. It's become a cultural touchstone, a symbol of quantum weirdness, showing up in cartoons and t-shirts and coffee mugs. But the original thought experiment was never meant to celebrate quantum mechanics. It was meant to show how absurd the theory seemed when you tried to apply it to everyday objects. Here's how it works. Imagine you put a cat in a sealed box along with a vial of poison, a radioactive atom, and a detector. If the atom decays, the detector triggers, the vial breaks, and the cat dies. If the atom doesn't decay, the cat lives. Now, according to quantum mechanics, before you measure it, the radioactive atom exists in a superposition, both decayed and not decayed simultaneously. And if the atom is in superposition, then the detector is too, both triggered and not triggered. And if the detector is in superposition, then so is the vial, both broken and intact. And if the vial is in superposition, then so is the cat, both alive and dead. at the same time, until you open the box and look. Schrödinger proposed this in 1935, and his tone was almost sarcastic. He was trying to show that something had gone wrong with quantum mechanics, that it couldn't possibly be the whole story, because cats are clearly either alive or dead. They're not in some ghostly in-between state. The thought experiment was a reductio ad absurdum, an attempt to prove quantum mechanics was incomplete by showing that its logic led to ridiculous conclusions. But here's the thing, the experiment never got performed with an actual cat, thankfully, but versions of it have been done with particles, with photons, even with small molecules. And every time the math works exactly as quantum mechanics predicts, the absurdity is real. Not with cats, perhaps. Cats are too big, too warm, too entangled with their environment for superposition to survive. But at smaller scales, like the universe really does maintain multiple contradictory states at once. So Schrödinger's cat, meant as a joke, as a criticism, ended up becoming one of the most famous illustrations of quantum mechanics. It reminds us that reality at the quantum level genuinely doesn't behave like the reality we navigate every day. And maybe that's okay. Maybe a universe that can hold contradictions in perfect balance, at least for a little while, is richer and stranger than one that always insists on definite answers. Picture yourself rolling a ball toward a hill. If you don't roll it hard enough, it rolls partway up, stops, and rolls back down. To get it over the hill, you need to give it enough energy to reach the top. That's how the classical world works. Energy barriers are absolute. You either have enough energy to cross them, or you don't. But in the quantum world, something remarkable happens. Particles can pass through energy barriers they shouldn't be able to cross. It's called quantum tunneling, and it's not cheating or finding a secret path. The particle doesn't go over the barrier or around it. It genuinely passes through, appearing on the other side even though it never had enough energy to climb over. How? Because particles aren't really particles in the classical sense. They're waves of probability, and waves can leak through barriers. Imagine a water wave hitting a dam. Most of the wave reflects back, but a tiny bit of water might seep through cracks and appear on the other side. Quantum tunneling is a bit like that, except there are no cracks. The particle's wave function, its cloud of probability, extends through the barrier, and there's a small chance that when you measure the particle, you'll find it on the far side. The thicker the barrier, the less likely tunneling becomes. The higher the barrier, the rarer the event. But it can happen, and it does happen, constantly all around you. In fact, you wouldn't exist without it. The atoms in your body contain electrons that have tunneled between energy states. The devices you use every day rely on electrons tunneling through barriers in semiconductors, and perhaps most beautiful of all, the sun shines because of quantum tunneling. Deep in its core, hydrogen nuclei are smashing together, trying to fuse into helium. But nuclei are positively charged, and positive charges repel each other with enormous force. The nuclei don't have quite enough energy to overcome that repulsion, to climb the energy hill and get close enough to fuse. According to classical physics, the sun should be dark and cold, but quantum mechanics allows tunneling. Some of those hydrogen nuclei, moving toward each other with not quite enough energy, tunnel through the electromagnetic barrier and fuse anyway. It's a rare event for any individual nucleus, but the sun has so many nuclei, so many collisions every second, that rare becomes routine. The light falling on your face, the warmth you feel on a summer day, the energy that powers all life on Earth, all of it exists because particles can sometimes be where they shouldn't be. passing through walls that should have held them back forever. Let's linger on that idea for just a moment longer, because it's worth the time. Everything you've ever eaten, every breath you've taken, every thought you've had, all of it traces back to the sun's light, and that light exists only because of quantum tunneling. Think about what that means. Without quantum mechanics, without the strange rule that lets particles pass through barriers, the sun would be a cold, dead ball of hydrogen. No fusion, no light, no warmth. Earth would be a frozen rock spinning in darkness. No oceans, no atmosphere, no life. None of this. No trees, no cities, no consciousness to wonder about how any of it works would exist. And it's not just our sun. Every star in the sky, every point of light scattered across the night, burns for the same reason. Quantum tunneling is what makes stars possible. It's what transforms clouds of hydrogen into furnaces of fusion, turning mass into energy, darkness into light. The entire visible universe, galaxies and nebulae, planets and moons, everything bright and beautiful, exists because of this one quantum phenomenon. There's something almost tender about that. The universe could have been built differently. The rules could have been strict, allowing no exceptions, no tunneling through barriers, and if they had been, the cosmos would be dark, silent, empty of anything like us. But the rules allow for a little uncertainty, a little probability leaking through impossible places, and that small allowance, that quantum permission, is enough to fill the universe with light. It's enough to make suns that warm worlds, worlds that grow life, life that eventually opens its eyes and looks back at the stars and wonders how it all works. You are, in a very real sense, made of stardust. But more than that, you're made possible by quantum tunneling. Your atoms were forged in dying stars, but those stars only lived because particles could tunnel. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it synthesized in stellar furnaces that burned because quantum mechanics permits the impossible. Perhaps that's worth thinking about as you drift towards sleep. Perhaps it's enough just to know that you're here because the universe allows for beautiful exceptions to its own rules. In 1935, Einstein co-authored a paper with two colleagues, Podolsky and Rosen, describing what they thought was a fatal flaw in quantum mechanics. They described a scenario where two particles become connected, entangled, in such a way that measuring one instantly affects the other. Yeah, no matter how far apart they are. You could separate them by inches or by light years, and still, the moment you measured one, the other would respond. Einstein found this absurd. He called it Spukhaft Fernwirkung, spooky action at a distance. It violated his deepest intuitions about how the universe should work. Nothing, according to his theory of relativity, can travel faster than light. No signal, no force, no information. And yet quantum entanglement seemed to allow for instantaneous connection across any distance. It was as if the universe had invisible threads connecting certain particles, threads that could stretch across galaxies without breaking or weakening. Einstein thought this proved quantum mechanics must be incomplete. There had to be hidden variables, some deeper reality that determined outcomes in advance, and making the connection only appear instantaneous. The particles weren't really communicating faster than light. They were just following a script written when they were created, like two letters sent in opposite directions containing the same message. But experiments have since proven Einstein wrong. Physicists have created entangled particles and measured them in ways that rule out hidden variables. The connection is real. Measure one particle's spin, and the other's spin is instantly determined, even if they're separated by miles. Change the measurement you perform on one, and the results you get from the other change accordingly, faster than any light speed signal could travel between them. And yet, and this is the subtle part, you can't use entanglement to send messages. The results you get from measuring entangled particles appear random. Only when you bring the two sets of results together and compare them do you see the correlation. So while something is happening faster than light, no information travels faster than light. It's as if the universe found a loophole in its own speed limit. What's actually happening? Nobody knows for certain. Some physicists think entangled particles aren't really separate. They're parts of a single quantum system that happens to be spread across space. Others think space-time itself might be woven from entanglement, with distance being a kind of illusion. Still others suspect we're asking the wrong questions, using concepts like here and there that don't apply to quantum systems. Einstein was right to call it spooky. It remains one of the strangest confirmed facts about reality. Two particles separated by any distance, maintaining a connection that seems to transcend space itself. Not communicating exactly, not signaling, just connected, sharing a state, being, in some deep sense, one thing rather than two, even when everything about our everyday experience says they should be separate. The universe, it seems, doesn't always respect the boundaries we draw around objects. Sometimes it insists that what looks like two is actually one, stretched thin across the cosmos. Let's think about entanglement a bit differently, because the usual explanation that measuring one particle affects the other makes it sound like telepathy, like some kind of signal passing between them. But that's not quite right. The truth is stranger and more subtle. When two particles are entangled, they don't each have their own separate quantum state. Instead, they share a single state, one mathematical description that encompasses both of them together. Before you measure either particle, neither one has a definite value for the property you're measuring. They exist in superposition in a state of undecided possibility. But their possibilities are linked, correlated, dancing together in a way that ensures when one becomes definite, the other does too. Imagine two coins, magically connected so that when you flip them both and look at the first one, whatever you see, heads or tails, the second coin will show the opposite. But before you look, neither coin is heads or tails. They're both in superposition, and their superpositions are locked together. The first coin is heads if the second is tails, and tails if the second is heads. When you finally look at one, both possibilities collapse simultaneously, across any distance, because they were never really two separate things. They were one joint state all along. This is less like telepathy and more like tearing a piece of paper in half. You put each half in an envelope and send them to opposite sides of the world. When someone opens one envelope and sees the left half, they instantly know the other envelope contains the right half. No signal travelled between envelopes. The correlation was established when you tore the paper, and it's just being revealed now. Except quantum entanglement is stranger than that, because with the paper, the left and right halves existed as definite things all along, even before anyone looked. With entangled particles, the properties literally don't exist until measured. It's as if the paper tears itself only when someone opens the first envelope, and in that same instant, the other piece appears in the distant envelope, already torn in the complementary way. Perhaps the lesson here is about separateness itself. We think of objects as fundamentally distinct. This particle here, that particle there, each going about its own business. But quantum mechanics suggests reality doesn't actually work that way. Things that have interacted, that have shared a history, remain connected in ways that transcend space. The universe remembers their relationship, preserves it, enforces it, no matter how far apart they drift. In a sense, nothing is truly separate. Everything has interacted with something else, and those interactions leave traces, invisible threads of correlation woven through space-time. We are all, in some quantum sense, entangled with the universe and with each other, connected by histories we've forgotten, but that nature quietly preserves. Here's something worth contemplating as you drift towards sleep. Quantum mechanics has been tested more rigorously, in more ways, across more conditions, than perhaps any other scientific theory in history. And it has never, not once, been proven wrong. Think about what that means. For over a century, physicists have been trying to break quantum mechanics, to find its limits, to discover situations where its predictions fail. They've tested it with atoms and molecules, with photons and electrons, with superconductors and semiconductors, at temperatures near absolute zero and at energies approaching the Big Bang, in laboratories and in particle accelerators, with devices the size of buildings and with circuits smaller than bacteria. Every single time, quantum mechanics has delivered the right answer. Not approximately, not close enough, exactly right, often to 10 or 15 decimal places. The theory predicts the energy levels of atoms with such precision that the predictions and measurements agree to better than 1 part in a trillion. It explains the magnetic moment of the electron, a measure of how strongly it responds to magnetic fields, accurately to 1 part in 100 billion. These aren't rough estimates. These are predictions so precise they're almost eerie. Imagine asking for directions and being told drive 3.14159265359 miles. That's the level of accuracy quantum mechanics routinely achieves, and it does this while describing a reality that seems, on its face, impossible. Particles in 2 places, waves acting like particles, measurements creating reality. It's strange, isn't it? The theory that seems most bizarre, most contrary to common sense, most likely to be approximation or metaphor, turns out to be the one that describes nature with almost perfect fidelity. Meanwhile, our intuitions, based on a lifetime of experience with medium-sized objects at medium speeds, fail completely at the quantum scale. Maybe there's a lesson there about truth. The universe isn't obligated to make sense to beings who evolve to hunt and gather, to avoid predators and find mates. Our intuitions were shaped by survival, not by accuracy about the deep structure of reality. So when our intuitions clash with experimental evidence, perhaps we should trust the evidence and be humble about our intuitions. Quantum mechanics works. That much is beyond dispute. Every technology that relies on it, every computer chip, every laser, every LED, every solar panel, functions exactly as quantum mechanics predicts. The theory may be strange, counterintuitive, philosophically disturbing, but it's also true in the most robust sense that science can establish truth, and there's something almost comforting about that. However weird the quantum world seems, at least we understand it well enough to describe it with mathematics that never lies. Your phone is a quantum device, so is your computer. The LED lights around you, was the GPS satellite helping navigate your city, the hard drive storing your photos, all of them work because of quantum mechanics. not because they're fancy or futuristic, but because you can't make modern electronics without understanding how electrons behave in atoms and semiconductors. Consider the transistor, the fundamental building block of every computer. Transistors are switches that control the flow of electricity, and modern processors contain billions of them, each one microscopically small. They work by exploiting quantum properties of silicon, how electrons move through different regions, how they tunnel through barriers, how they occupy different energy levels. Classical physics can't explain transistor behavior. You need quantum mechanics to understand why they work at all, or think about lasers. The word itself is an acronym: light amplification by stimulated emission of radiation, and that stimulated emission is a purely quantum phenomenon. Atoms absorb light when electrons jump to higher energy levels, and emit light when electrons fall back down. But in a laser, you carefully arrange things so that when one atom emits a photon, it triggers nearby atoms to emit photons too. Photons with exactly the same wavelength, exactly the same phase, all marching together in lockstep. That synchronized emission is impossible in classical physics. It requires quantum mechanics to explain and engineer. Even the hardness of matter, the fact that you can't push your hand through a table, is quantum mechanical. It's the Pauli exclusion principle, which we'll get to later, that prevents atoms from overlapping. Any classical physics would allow atoms to pass through each other like ghosts. Quantum mechanics provides the solidity. So when we talk about quantum mechanics being strange and abstract, it's worth remembering. You are surrounded by quantum technology. You use it every day. Your entire modern life, communication, computation, illumination, navigation, rests on a foundation of quantum effects that were considered bizarre philosophical curiosities just 100 years ago. The inventors of quantum mechanics didn't set out to create smartphones or GPS. They were trying to understand why heated objects glow, why atoms are stable, how light interacts with matter. They were pursuing curiosity, seeking truth for its own sake, and in doing so they accidentally handed humanity the keys to the information age. Perhaps there's a pattern there. Perhaps the most transformative technologies always emerge from basic research, from questions asked simply because we want to know the answer. Perhaps the universe rewards curiosity not just with understanding, but with power. The power to reshape the world in ways the questioners never imagined. Here's a question that should have bothered anyone who learned about atoms. Why don't they collapse? Think about it. An atom is mostly empty space, a tiny nucleus surrounded by even tinier electrons, and those electrons are negatively charged, while the nucleus is positively charged. Opposite charges attract. So why don't the electrons just spiral inward, crash into the nucleus, and end the whole affair in a fraction of a second? Classical physics has no good answer. According to Maxwell's equations, here a charged particle moving in a circle, like an electron orbiting a nucleus, should radiate energy away as electromagnetic waves. It should lose energy, spiral inward, and hit the nucleus in about 100 trillionth of a second. Every atom in the universe should collapse almost instantly. Matter shouldn't be stable. Nothing should exist. But matter does exist. Atoms are stable. You're made of them, and you're not collapsing into a point. So something must be preventing that spiral of doom. And that something is quantum mechanics. Remember that electrons don't orbit. They exist in probability clouds, in specific energy levels that are quantized. They come in discrete steps, not a smooth continuum. An electron in an atom can only occupy certain allowed states. It can't have just any energy. It can only have specific energies corresponding to specific orbitals, and crucially, there's a lowest energy level, the ground state, and an electron in that state can't fall any lower because there's nowhere lower to fall to. It's like being on the ground floor of a building. You can go up the stairs to higher floors, but you can't go down from the ground floor. There's no basement. Electrons in the ground state are already at the bottom. They can't radiate away more energy because they don't have any more energy to give. They're stable not because some force is holding them up, but because quantum mechanics simply doesn't allow them to exist at lower energies. This is why matter is solid, why atoms persist, why chemistry happens. If electrons could occupy arbitrary energy levels, they'd all cascade down to the nucleus and everything would collapse. But quantum mechanics says no, energy levels are quantized, there's a ground state, and once you're there, you stay there. So every object around you, every wall, every chair, every cell in your body exists because of this quantum fact. Stability isn't the natural state of things. Collapse should be. But quantum mechanics intervenes, drawing a line and saying this far and no farther. And because of that intervention, the universe can have persistent structures, atoms that last, molecules that form, life that evolves, minds that wonder why any of it exists at all. Photons are strange messengers. They're particles of light, quantum packets of electromagnetic energy, and yet they have no mass at all, not a tiny mass, not an almost zero mass, actually genuinely zero. No, they're pure energy in motion, travelling through space at the universe's speed limit. And here's the beautiful paradox. They travel at the speed of light precisely because they have no mass. In Einstein's special relativity, anything with mass requires infinite energy to reach light speed. It's impossible. But photons, being massless, can't travel at any other speed. They're born moving at light speed, they live their entire existence at light speed, and if they ever stopped, they would cease to exist. From a photon's perspective, if we can speak of such a thing, no time passes at all. Because of time dilation, at light speed, clocks stop. A photon emitted from a distant star and absorbed by your eye experiences no duration between emission and absorption. From its reference frame, the entire journey is instantaneous. His birth and death happen in the same timeless moment, yet photons carry energy and momentum. They can push on things, exert pressure, transfer motion. Solar sails work by catching the momentum of photons from the sun. Your eye detects photons by absorbing their energy. Radio antennas receive photons with wavelengths meters long. X-ray machines emit photons energetic enough to pass through flesh. All photons, just with different energies. The energy of a photon depends on its frequency, how many times per second its electromagnetic wave oscillates. High-frequency photons, like gamma rays, carry enormous energy. Low-frequency photons, like radio waves, carry very little. But all photons, regardless of energy, travel at exactly the same speed. A radio photon and a gamma-ray photon, racing across empty space, would stay perfectly synchronized. The universe doesn't play favorites, and photons don't age, they don't decay. A photon from the cosmic microwave background, travelling for 13.8 billion years since the Big Bang, is still exactly the same photon it was when it started. Unchanged, undiminished, carrying the same energy it had when the universe was young and hot and filled with light. In a sense, photons are immortal, at least until they're absorbed by something, transferred into heat or chemical reactions or the electrical signals in your retina. There's something almost ethereal about them. Massless, timeless, ageless, pure energy in its simplest form threading through the cosmos, connecting distant things, a star and your eye, a phone tower and your device. The early universe and telescopes pointed at the sky. Photons are the universe's way of sharing information across space, of making distant things visible, of letting separated parts of reality touch each other without ever meeting. Maybe that's why light has always felt mysterious, magical, sacred. Long before anyone understood photons or quantum mechanics, humans knew that light was special, that it revealed, illuminated, connected. And now we know it's even stranger than our ancestors imagined. Not a wave in some medium, not a substance flowing through space, but massless particles that experience no time, carrying energy at the universe's ultimate speed, making the invisible visible. If you want to see quantum strangeness with your own eyes, or at least see its undeniable effects, the double-slit experiment is where to look. It's been called the central mystery of quantum mechanics, the one experiment that captures all the weirdness in a single demonstration. Here's how it works. You take a barrier with 2 narrow slits in it, and you shine light at it. Some light passes through the slits and hits a screen behind the barrier. What pattern do you see? Not 2 bright strips corresponding to the 2 slits. Instead, you see many strips, an interference pattern of alternating bright and dark bands. This makes sense if light is a wave. Waves passing through 2 slits spread out and overlap on the other side. Where 2 wave peaks meet, they add together, bright. Where a peak meets a trough, they cancel out, dark. The interference pattern proves light behaves like a wave, easy enough. But now dim the light way down. Send photons one at a time so that only 1 photon is travelling through the apparatus at any moment. Now what happens? Each photon hits the screen at a single point, a tiny dot of light, particle-like. But over time, as thousands of individual photons arrive one by one, dots accumulating, they form the same interference pattern, stripes of many dots alternating with stripes of few dots. How can 1 photon create an interference pattern? It's not interfering with other photons. There are no other photons. It arrives alone, and yet somehow it knows about both slits. It behaves as if it passed through both slits simultaneously, interfered with itself, and then chose a place to land based on that interference. But wait, it gets stranger. Set up detectors at the slits to see which one each photon actually passes through. Now watch what happens. The interference pattern disappears. When you measure which slit the photon goes through, it picks 1 slit, goes through that slit alone, and you get 2 simple strips on the screen, no interference. The act of observing which path the photon took changes what pattern emerges. It's as if the photon knows you're watching. When you don't look, it behaves like a wave, explores both possibilities, creates interference. When you do look, it behaves like a particle, picks 1 path, and the interference vanishes. The universe responds to observation, adjusting reality based on what you choose to measure. Physicists have run this experiment thousands of ways, with electrons, neutrons, even large molecules. Same result every time. Observation matters. The act of measurement doesn't just reveal reality, it participates in creating it. And nobody knows why. There's no hidden mechanism, no classical explanation. Yeah, it's just how things are at the quantum level. Maybe the lesson is that reality is more participatory than we thought. We're not just passive observers watching a pre-existing world. We're part of the system, and our choices about what to measure shape what becomes actual. The universe doesn't exist out there independent of observation. It's a conversation between observer and observed, measurement and measured, each influencing the other in ways we're still trying to understand. Every colour you've ever seen, the blue of the sky, the green of grass, the red of blood, the gold of autumn leaves, exists because of quantum mechanics. Colour isn't painted onto objects. It emerges from how electrons in atoms interact with light, and that interaction is purely quantum. Here's what happens. Light is made of photons, as each carrying a specific amount of energy determined by its wavelength. When light hits an atom, electrons can absorb photons, but only photons whose energy exactly matches the energy difference between two electron orbitals. If the energy doesn't match, the photon passes by without being absorbed. So when white light, containing all wavelengths, hits an object, some wavelengths get absorbed. Their energy matches electron transitions, and some get reflected. No matching transitions available. The reflected wavelengths are what you see as colour. A red apple absorbs blue and green light, reflects red. Grass absorbs red and blue, reflects green. The sky scatters blue light more than other wavelengths, painting it blue. But why do specific electron transitions absorb specific energies? Because electron orbitals in atoms are quantized. They come in discrete energy levels, not a smooth continuum. An electron in one orbital can jump to a higher orbital only if it absorbs exactly the right amount of energy. Too little, and the jump can't happen. Too much, and there's leftover energy with nowhere to go. It has to be exact. This is why emission spectra are so useful in astronomy. When you heat an element, electrons jump to higher orbitals. When they fall back down, they emit light. Photons with energies exactly matching the orbital differences. Each element has its own unique set of orbitals, so each element emits its own unique set of wavelengths. Hydrogen's spectrum looks different from helium's, which looks different from carbon's. By analysing the light from distant stars, astronomers can determine what those stars are made of, even though they're trillions of miles away. The light carries a fingerprint, a quantum signature written in wavelengths, revealing the composition of objects we can never touch. It's like being able to identify a person by their voice, except the voice is the specific pattern of energies an atom can emit. And all of this, every shade, every hue, every subtle gradation of colour in the world around you, traces back to quantized electron orbitals. If energy levels were continuous rather than discrete, colours would blur together. There would be no sharp absorption lines, no unique spectral fingerprints, no way to identify elements by their light. The universe would be less knowable, less structured, less rich. So when you watch a sunset, when you admire a painting, when you notice the deep blue of twilight giving way to the black of night, you're seeing quantum mechanics in action. You're seeing the discrete nature of energy levels, the specific transitions electrons can make, the photons that survive those transitions and reach your eye. Colour is quantum. Beauty, at least in this sense, is quantized. Even at absolute zero, the coldest possible temperature, where all thermal motion should cease, quantum systems never completely stop moving. There's always a little jiggle left, a residual motion that can't be removed. It's called zero-point energy, and it exists because of the uncertainty principle. Remember, the uncertainty principle says you can't know both position and momentum with perfect precision. If a particle were completely at rest, zero momentum are perfectly still, you'd know its momentum exactly, and if you knew its momentum exactly, the uncertainty principle would demand infinite uncertainty in its position. The particle could be anywhere in the universe, which is absurd. So even in its lowest energy state, even at absolute zero, a particle must have some motion. Not much, just enough to satisfy the uncertainty principle. Its position must be a bit fuzzy, which means it must be moving slightly. It's as if the universe imposes a minimum tax on existence, a ground rent that all particles must pay in the form of perpetual motion. This isn't theoretical. Zero-point energy has observable effects. Liquid helium, even at temperatures just a fraction of a degree above absolute zero, doesn't freeze solid. The helium atoms have enough zero-point motion to remain liquid, though you'd have to apply enormous pressure to force it to solidify, because quantum mechanics insists the atoms keep moving. And remember those virtual particles we mentioned, the ones constantly appearing and disappearing in empty space. They're powered by zero-point energy. The vacuum isn't empty, it's a seething foam of quantum activity, particles borrowing energy from the uncertainty principle for brief moments before paying it back. This activity produces real, measurable forces like the Casimir effect, where two metal plates placed very close together in a vacuum experience an attractive force, because they restrict which virtual particles can exist between them. There's something oddly comforting about zero-point energy. It means the universe never completely stops. There's no state of perfect stillness, no absolute death. Even in the coldest, darkest, most isolated corner of space, quantum fluctuations persist. The universe hums with a minimum level of activity, a baseline creativity that can never be suppressed. Perhaps it's a reminder that absolute nothing doesn't exist, that emptiness is impossible, that even when you take everything away, all heat, all light, all particles, quantum mechanics still demands something remain, a whisper of motion, a ghost of possibility. The universe refusing to be truly, finally, completely still. When will a radioactive atom decay? You can't know, not because you lack information, not because the calculation is too complex, but because the universe itself doesn't know. It hasn't decided yet. Radioactive decay is one of the few processes in nature that's genuinely, fundamentally random. And scientists can tell you the half-life of a radioactive isotope, the time it takes for half the atoms in a sample to decay. Carbon-14 has a half-life of about 5,730 years. Uranium-238 has a half-life of 4.5 billion years. Those statistics are rock-solid, predictable, useful, but ask when a specific atom will decay, and there's no answer. It might decay in the next second. It might last 1,000,000 years. There's a probability, but no certainty. This is what Einstein couldn't accept. He believed in determinism, the idea that if you knew everything about a system, you could predict its future perfectly. God does not play dice, he insisted. But radioactive decay proves that at least in this case, dice are exactly what's being played. An unstable nucleus exists in a quantum state, a superposition of not yet decayed and decayed. Over time, the probability of decay increases, but the exact moment is undetermined. It's not that some hidden clock is ticking down inside each atom, counting toward a predetermined moment. The atom genuinely doesn't have a set decay time. The moment of decay is created when it happens, not discovered. And when decay finally occurs, it's spontaneous, no trigger, no cause in the usual sense. The atom just decides, randomly, following probabilities but not rules. It's as if the universe is rolling dice billions of times per second for every radioactive atom, and when the dice come up right, decay happens. This fundamental randomness has practical implications. Carbon dating works because carbon-14 decays at a known average rate. Smoke detectors contain tiny amounts of americium-241, which decays and emits particles that ionize air, allowing current to flow until smoke interrupts it. Nuclear medicine uses radioactive isotopes that decay inside your body, emitting radiation that doctors can detect to see how organs function. But philosophically, radioactive decay is revolutionary. It proves the universe isn't a clockwork mechanism where the future is inevitable, just waiting to unfold. There are events with no prior cause, outcomes without predetermination, true chance woven into reality's fabric. Maybe that's unsettling. Maybe it's liberating. The universe isn't a rigid script being performed. It's improvisational, creative, genuinely open to possibilities that haven't yet been chosen. And in that openness, in that fundamental randomness, there's room for something other than mechanical inevitability, room for surprise, for novelty, for the genuinely new to emerge from the quantum foam and declare itself into existence. Here's a question that sounds absurd until you think about it. Why can't you walk through walls? Why does matter have solidity at all? Atoms are mostly empty space. The nucleus is tiny. The electrons are tinier, and the vast distance between them is just nothing. If you could shrink the nucleus of a hydrogen atom to the size of a marble, the electron would be orbiting about half a mile away. Everything in between is vacuum. So when you sit in a chair, you're really just empty space sitting on empty space. The atoms in your body and the atoms in the chair are mostly void. They should pass through each other like galaxies passing in the night, barely noticing each other's presence, but they don't. The chair feels solid, impenetrable, real. So the answer is quantum mechanics, specifically the electromagnetic force combined with something called the Pauli exclusion principle. When your atoms get close to the chair's atoms, the electron clouds start to overlap. And here's where quantum rules become crucial. Electrons are fermions, particles with half-integer spin, and the Pauli exclusion principle states that no two identical fermions can occupy the same quantum state simultaneously. In practical terms, this means electrons resist being in the same place. When the electron cloud around your atoms tries to overlap with the electron cloud around the chair's atoms, quantum mechanics says no. The electrons repel each other, not because of electric charge alone, but because they're forbidden from sharing the same state. It's an absolute prohibition, written into the fabric of reality. But this resistance, this quantum prohibition against overlapping, is what you feel as solidity. When you push on a wall, you're not actually touching it in the classical sense. The electron clouds in your hand and the wall are repelling each other through electromagnetic forces and Pauli exclusion, creating what feels like contact but is really mutual rejection at the quantum level. And it's strong. Try to push two atoms too close together and the resistance increases enormously. The electrons would rather do almost anything than violate the exclusion principle. This is why matter doesn't collapse, why you can stack books and build bridges and stand on the ground without sinking through. In a way, all of solid matter, every structure ever built, every tool ever held, every handshake ever shared, is held up by a quantum rule. Not by physical barriers, but by a mathematical prohibition. You exist in the shape you do, separate from your chair, separate from the ground, separate from other people, because quantum mechanics draws invisible boundaries that cannot be crossed. There's something both beautiful and lonely about that. We're all quantum mechanically isolated, never truly touching anything, held apart by rules that operate at scales we can't see. And yet that isolation is what gives reality its structure, its separateness, its ability to have distinct objects at all. Without the Pauli exclusion principle, matter would collapse into an undifferentiated blur. So perhaps the price of being a distinct thing, a separate self, is precisely this quantum loneliness, this inability to ever truly merge with anything else. Let's go deeper still. What is a particle? Really, you might picture a tiny ball, a speck of matter, something localized and definite. But quantum field theory, our most complete description of particles, says something stranger. Particles aren't really particles at all. They're excitations in underlying fields that permeate all of space. Think of reality as an ocean, except instead of one ocean of water, there are multiple oceans overlapping, an electron field, a photon field, a quark field, and so on. These fields exist everywhere, throughout all of space, even in what we call vacuum. They're like invisible fluids, each vibrating with its own character. A particle is what happens when one of these fields gets excited, when energy creates a ripple, a wave, a disturbance in the field. An electron isn't a tiny ball moving through the electron field. It is a localized vibration of the electron field itself. A photon is a ripple in the electromagnetic field. A quark is an excitation in the quark field. When you see an electron moving, you're watching a wave of excitation propagate through the electron field. The way a wave moves across the ocean, the wave looks like it's traveling, like it's a thing moving from here to there, but really it's just the field oscillating, energy transferring from one region to another. This perspective changes everything. It means empty space isn't empty. It's full of fields, quiet and unexcited, but present everywhere. It means particles can be created from nothing, as long as you add enough energy to excite the field. It means particles can disappear, their energy returning to the field, the excitation fading away. Well, and it explains something that otherwise seems magical, why every electron in the universe is identical. If electrons were little balls made in factories, you'd expect some variation. This one slightly heavier, that one slightly different. But all electrons have exactly the same mass, exactly the same charge, exactly the same properties. Why? Because they're all excitations of the same field. An electron in your body and an electron in a distant star are both ripples in one universal electron field, so of course they're identical. They're the same kind of wave in the same medium. This view also makes quantum creation and annihilation more natural. When an electron and a positron, its antiparticle, meet and annihilate, they're not destroying matter. They're just two complementary excitations in the electron field cancelling each other out, like waves meeting and flattening. The energy goes into other fields, creating photons, excitations in the electromagnetic field. Nothing is lost. The ocean just transfers energy from one wave pattern to another. Perhaps this is the deepest description of reality we have. Not objects moving through space, but fields vibrating in patterns we interpret as particles. Not stuff, but activity. Not things, but processes. Reality as verb rather than noun, as continuous becoming rather than static being. The universe as music, fields humming at different frequencies, harmonizing and clashing, creating the symphony of existence. For every particle in the universe, there exists an antiparticle, a mirror twin with opposite properties. Electrons have positrons, with the same mass but positive charge instead of negative. Protons have antiprotons. There's negative where protons are positive. Even neutral particles like neutrons have antineutrons, identical in mass but different in subtle quantum properties. Antimatter isn't science fiction. It's real, predicted by quantum mechanics and confirmed by experiment. In 1928, Paul Dirac was solving equations describing how electrons behave, according to both quantum mechanics and special relativity. The math kept giving him two solutions, one for normal electrons and one for mysterious particles with negative energy. At first, Dirac thought these were mistakes, mathematical artifacts with no physical meaning, but he couldn't make them go away. The equations insisted, if electrons exist, something else must exist too. In 1932, physicists detected positrons in cosmic rays, particles with the same mass as electrons but opposite charge. And Dirac's mistake was real. Antimatter existed, and it has a spectacular property. When matter meets antimatter, they annihilate. An electron and a positron that touch each other disappear in a flash of pure energy. Two photons shooting away in opposite directions, carrying the mass energy of the destroyed particles. E equals mc squared in action, matter converting completely to energy. This seems like a recipe for disaster. If antimatter exists, and it annihilates with matter, why is there any matter left in the universe? The Big Bang should have created equal amounts of matter and antimatter. They should have found each other and annihilated completely, leaving nothing but light. But we exist. The universe is full of matter and nearly empty of antimatter. And something tipped the balance. Some asymmetry in the early universe that created slightly more matter than antimatter. Perhaps one extra matter particle for every billion matter-antimatter pairs. Those billion pairs annihilated, filling the early universe with radiation. The tiny excess, the one particle in a billion, survived. Everything you see, including yourself, is that excess, the leftover, the imperfection in the universe's symmetry. We don't fully understand why the asymmetry exists. It's one of the great mysteries in physics. The laws we know are symmetric. They treat matter and antimatter equally, yet the universe clearly favours matter. Somewhere in the first moments after the Big Bang, something broke that symmetry. Some process, some interaction, some quirk of quantum mechanics or cosmic evolution chose matter over antimatter. And thank whatever it was that it did, because without that tiny bias, that one part in a billion favoritism, nothing would exist except photons. No atoms, no stars, no planets, no life. Just light, forever in an empty cosmos. We're the children of asymmetry, the descendants of imbalance, survivors of an annihilation that should have been total but wasn't quite. We talked earlier about quantum entanglement, how two particles can share a state so that measuring one instantly affects the other, regardless of distance. But there's a subtlety worth exploring. Entanglement doesn't actually let you send information faster than light. This seems contradictory. If measuring one entangled particle instantly determines the state of its partner across the galaxy, aren't you transmitting information instantaneously? Couldn't you use this to build a faster-than-light telegraph, encoding messages in quantum measurements? The answer is no, and here's why. The results you get from measuring an entangled particle look completely random. Imagine you have an entangled pair of particles, each with quantum spin that could be up or down. You measure yours and get up. Because of entanglement, your partner's particle is now definitely down. But you had no control over getting up. It was random. And the person holding the other particle, when they measure it and get down, has no way to know whether their result was random or caused by your measurement. Only when you bring your results together and compare them do you see the correlation. Your ups correspond to their downs, your downs to their ups, with perfect reliability. The connection is real. But you can't use it to send a message because neither side can control what they measure, and neither side can tell whether the other has measured yet. It's like having two magic coins, connected so that whenever one comes up heads, the other comes up tails. You flip yours, get heads, and instantly know your partner got tails. But your partner, looking at tails, can't tell whether you've flipped yet or not. Their result looks random either way. To discover the correlation, you'd have to call them on a regular phone and compare results. Communication at light speed or slower, not faster. So entanglement is real. The connection is instant, but information transfer requires classical communication afterward. Nature seems to have found a loophole. Quantum correlations can be non-local, but causality and information remain safely bound by the speed of light. There's something elegant about this. The universe permits spooky action at a distance, but not in a way that breaks causality. It allows particles to remain connected across space, but not in a way that violates relativity's speed limit. It's as if reality has multiple rules that seem to conflict, nothing faster than light, yet entanglement is instant, and somehow manages to satisfy both simultaneously through careful design. Perhaps the lesson is about connection and isolation. We can be correlated with distant things, connected in ways that transcend space, and yet still fundamentally unable to communicate faster than light allows. The universe permits relationship, permits deep quantum connection, but preserves a certain isolation too, a limit on how quickly information can propagate, how fast causes can produce effects. We're connected and separate both at once, in ways that respect both our need for relationship and the universe's need for order. All of quantum mechanics culminates in something called the Standard Model, a theory that describes all known particles and 3 of the 4 fundamental forces. It's the most complete description of reality's building blocks we have, built entirely on quantum field theory, confirmed by countless experiments, and yet still somehow not the final word. The Standard Model tells us there are 2 types of fundamental particles: fermions, which make up matter, and bosons, which carry forces. The fermions include quarks, which combine to form protons and neutrons, and leptons, which include electrons and neutrinos. The bosons include photons, carrying electromagnetic force, W and Z bosons, carrying the weak nuclear force, and gluons, carrying the strong nuclear force that holds atomic nuclei together. These particles interact by exchanging force-carrying bosons. When 2 electrons repel each other, they're exchanging photons, virtual photons that pop into existence, carry force, and disappear again. When a neutron decays into a proton, electron, and neutrino, a W boson is involved, mediating the transformation. Forces, in the quantum view, aren't invisible pulls or pushes. They're particle exchanges, quantum transactions happening too fast to see. And the predictions are astonishing. The Standard Model explains the magnetic moment of the electron to 11 decimal places. It predicted the existence of the W and Z bosons before they were discovered. It predicted the top quark, the tau neutrino, and most famously the Higgs boson. a particle that gives other particles mass discovered in 2012 after decades of searching. But the Standard Model isn't complete. It doesn't include gravity, which remains stubbornly incompatible with quantum mechanics. It doesn't explain dark matter or dark energy, which together make up 95% of the universe's content. It doesn't tell us why particles have the masses they do, or why there are 3 generations of quarks and leptons instead of 1 or 10. Still, for everything it does describe, the behavior of matter at accessible energies, the forces that structure atoms and nuclei, the particles that make up everything we can touch, the Standard Model works flawlessly. It's a monument to human understanding, a framework that reveals the quantum architecture underlying all visible reality, and it's incomplete. Gloriously, frustratingly incomplete. Which means there's more to discover, deeper layers to uncover, new physics waiting beyond the edges of what we know. The Standard Model is perhaps the most successful scientific theory ever built, and yet it's also clearly not the end of the story. Just another chapter in an ongoing conversation between curiosity and cosmos, question and answer, mystery and revelation. We've talked about the uncertainty principle as it applies to position and momentum, how knowing one precisely makes the other fuzzy. But there's another version of this principle, equally profound and perhaps even more unsettling, the uncertainty relationship between time and energy. In quantum mechanics, the more precisely you try to measure when something happens, the less precisely you can know the energy involved, and conversely, the more accurately you measure energy, the less certain you can be about timing. It's as if the universe has a fixed budget of certainty, and you can spend it on time or energy, but not fully on both. This has strange consequences. For very brief moments, tiny fractions of a second, the uncertainty in energy becomes large. So large that particles can essentially borrow energy from the vacuum, bringing virtual particles into existence for fleeting instants. These particles exist in violation of energy conservation, but only briefly. The shorter the time, the larger the energy violation the universe permits. It's like having a bank account where you can overdraw by any amount as long as you pay it back quickly enough. Borrow a little, and you can keep it for a while. Borrow a lot, and you'd better return it almost instantly. The universe balances its books, but it allows temporary loans against future deposits. This time-energy uncertainty also affects measurements. Trying to measure the exact moment a radioactive atom decays, the precision of that timing measurement limits how accurately you can know the energy of the emitted particle. Trying to measure the exact energy of a photon, you need to observe it for a certain duration, which introduces uncertainty about exactly when it had that energy. In a way, time and energy are entangled at a fundamental level. Not in the sense of quantum entanglement, but in the sense that they trade off against each other, constrain each other, define each other's limits. You can't have infinite precision in both. The universe won't allow it. Perhaps there's a deeper message here about duration and existence. To exist with a definite energy, a particle needs time, needs to persist long enough that its energy can be measured. Things that exist only briefly must be uncertain about their energy, and conversely, things with very precise energy must have indefinite timing, existing in a kind of temporal blur. Reality, it seems, isn't made of instantaneous snapshots with perfect information. It's made of durations, of processes that take time. And in that taking time, there's always a negotiation between what can be known about when and what can be known about how much energy. The universe is less like a photograph and more like a slightly out-of-focus movie, where sharpening one aspect inevitably blurs another. For decades, quantum mechanics was seen as the physics of the very small, atoms, electrons, photons, with no relevance to biology or living systems. Life operates at warm, wet, messy scales, where quantum effects should be washed out by thermal noise and decoherence, or so everyone thought. But nature, it turns out, has been using quantum mechanics for hundreds of millions of years. We're just now discovering how. Consider migratory birds, species that fly thousands of miles, navigating with remarkable precision using Earth's magnetic field. How do they sense that field? The leading theory involves quantum entanglement happening inside proteins in their eyes. Here's how it might work. Light entering a bird's eye can create pairs of electrons in certain molecules, and these electrons become entangled. Earth's magnetic field influences how quickly the entanglement breaks down, how long it lasts before decoherence destroys it. Different orientations of the bird's head relative to the magnetic field produce different decoherence rates, which the bird's visual system can detect. The bird literally sees the magnetic field as a pattern of light and shadow overlaying its normal vision. This is astonishing. Entanglement is supposed to be fragile, destroyed instantly by any interaction with a warm environment. And yet birds' eyes, warm, full of jostling molecules, and constantly bathed in light, somehow maintain entanglement long enough to be useful. Their biological quantum sensors evolved naturally operating at body temperature. And it's not just birds. There's growing evidence that photosynthesis, the process by which plants convert sunlight to chemical energy, uses quantum coherence. When a photon hits a light-harvesting complex in a chloroplast, the energy needs to find its way to the reaction center where it can be used. Classical physics suggests the energy would random walk through the complex, bouncing around inefficiently. But experiments suggest the energy explores multiple pathways simultaneously, in quantum superposition, finding the optimal route with near-perfect efficiency. It's as if the plant is running a quantum computer, testing all possible paths at once and choosing the best one, or all in a messy, warm, wet biological environment where quantum effect should be impossible. We're still piecing this together. Quantum biology is young, controversial, not yet fully proven. But if it's real, if life has been harnessing quantum effects all along, it changes our understanding of both biology and quantum mechanics. It suggests that the line between quantum and classical isn't as sharp as we thought, that quantum effects can survive in warm, complex systems if evolution finds the right molecular architectures. Perhaps life is inherently quantum. Perhaps the exquisite sensitivity, the information processing, the energy efficiency that living things display requires quantum mechanics at some level. Perhaps we're all quantum systems, just very large and complex ones, and our existence depends on effects we're only beginning to understand. Here's something wonderfully paradoxical. If you watch a quantum system continuously, you can prevent it from changing. It's called the quantum Zeno effect, named after the ancient Greek philosopher Zeno and his paradoxes about motion. Remember that quantum systems evolve through superposition. They spread out into multiple possibilities, and then measurement collapses them to one outcome. But what if you measure constantly? What if you check the system over and over, giving it no time to evolve between measurements? Each measurement collapses the system back to its initial state, and if you measure frequently enough, the system never has time to evolve away from that state before being collapsed back to it. It's like trying to leave a room. Yeah, but every time you take a step toward the door, someone shouts, "Stay there!" and you snap back to where you started. This has been demonstrated experimentally with radioactive atoms. Normally, an unstable atom in an excited state will eventually decay, dropping to a lower energy state and emitting a photon. But if you measure whether it has decayed yet, and you measure very frequently, you can dramatically slow down or even prevent the decay. The act of repeated observation freezes the atom in its excited state. It's not that measurement is physically holding the atom in place, it's that each measurement collapses the atom's wave function to not yet decayed, and between measurements, there isn't enough time for the wave function to evolve significantly toward the decayed state. The quantum-watched pot genuinely never boils. There's something almost mystical about this. Observation affecting reality is one thing. We've accepted that quantum measurements have consequences. But observation preventing change? That feels like a different order of strangeness. It's as if the universe needs privacy to evolve, and constant watching interferes with processes that would otherwise unfold naturally. In practical terms, the quantum Zeno effect is weak. You need incredibly frequent measurements to see it clearly. But conceptually, it's profound. It suggests that the flow of time, the evolution of systems, the unfolding of possibilities into actualities, all of this can be influenced by observation. Not by doing anything to the system, just by looking, watching, paying attention. Perhaps there's a metaphor here about attention and change. In our own lives, a constant self-monitoring, endless checking and measuring can sometimes freeze us, prevent the natural evolution that would happen if we just let ourselves be for a while. Growth requires a certain amount of non-observation, of allowing processes to unfold without constant interference. The quantum Zeno effect, oddly enough, might be teaching us something about the value of not looking, of trusting that systems, even our own lives, can evolve properly without constant measurement. In 1964, physicist John Bell proved something remarkable. Quantum mechanics cannot be explained by hidden variables. Einstein had hoped that the apparent randomness and non-locality of quantum mechanics were just artifacts of incomplete information, that there were hidden properties unknown to us, that determined quantum outcomes in a deterministic way, and Bell proved this couldn't be true. Here's the essence of Bell's argument. He constructed a mathematical inequality, now called Bell's inequality, that must be satisfied by any theory based on local hidden variables. Local means no faster than light influences. Hidden variables means properties that exist whether or not we measure them. Any theory where reality is both local and deterministic must satisfy Bell's inequality. Then he showed that quantum mechanics predicts violations of Bell's inequality. According to quantum mechanics, entangled particles should correlate in ways that are too strong, too perfect, to be explained by any local hidden variable theory. If quantum mechanics is right, Bell's inequality must be violated. So physicists did the experiments. Over and over, in increasingly sophisticated ways, they created entangled particles and measured their correlations, and every single time, the results violated Bell's inequality, exactly as quantum mechanics predicted. This means something profound. The universe is not both local and deterministic. Either faster than light influences exist, violating locality, or quantum randomness is fundamental, and not the result of hidden information violating determinism, or both. Most physicists accept that quantum randomness is real, that particles genuinely don't have definite properties before measurement, that outcomes are truly undetermined. The alternative, faster-than-light hidden influences, seems more bizarre and less supported by evidence, though it remains a minority view. Bell's theorem closed a door that Einstein had hoped to walk through. It proved that quantum mechanics isn't just a provisional theory, waiting to be replaced by something more intuitive and deterministic. The weirdness is real. The randomness is fundamental. The universe at its base is not a clockwork mechanism, and there's something almost liberating about that. The future is not predetermined. Outcomes are genuinely open. When a quantum measurement happens, something new comes into being. Not revealed, but created. The universe is participatory, improvisational, alive in a way that strict determinism would never allow. Perhaps Bell's theorem is telling us that reality is inherently creative, that it generates novelty, makes genuine choices, brings forth possibilities that didn't exist before. And if the universe can do that at the quantum level, perhaps we, complex quantum systems ourselves, can too. Perhaps our choices, our decisions, our moments of uncertainty aren't just illusions of ignorance, but participations in the universe's fundamental openness. One of the most beautiful applications of quantum mechanics is quantum cryptography, using the laws of physics to create absolutely unbreakable codes. Not unbreakable because we're clever, but unbreakable because nature itself guarantees it. Here's how it works. Remember that measuring a quantum system disturbs it. You can't observe a quantum state without changing it. This fact, which seems like a limitation, becomes a security feature in quantum cryptography. Imagine two people, traditionally called Alice and Bob, who want to share a secret key they can use to encrypt messages. Alice sends Bob a stream of photons, each polarized in a random direction, up, down, left, right, or at diagonal angles. These polarizations can represent ones and zeros, encoding a random string of bits. Bob measures each photon's polarization. But here's the clever part. He doesn't know which basis Alice used for each photon, so he guesses, measuring some photons in the up-down basis, others in the diagonal basis. Sometimes he guesses right, sometimes wrong. After the transmission, Alice and Bob communicate publicly, on a normal channel that anyone can hear, about which basis they each used for each photon. They discard the photons where Bob guessed the wrong basis and keep only the ones where he guessed correctly. The remaining bits form their shared secret key. Now, what if an eavesdropper, traditionally called Eve, tries to intercept the photons? She'd have to measure them to learn anything, but measuring changes the quantum states. When Bob measures his photons, some of them will give unexpected results because Eve's measurements disturbed them. Alice and Bob, comparing a random sample of their bits publicly, will notice mismatches that reveal Eve's presence. The laws of quantum mechanics guarantee that any eavesdropping attempt leaves detectable traces. You cannot copy unknown quantum states, a result called the no-cloning theorem. You cannot measure them without disturbance. So any attempt to intercept the message inevitably alerts the legitimate parties. This isn't security through obscurity or complexity, it's security through physics. Even if Eve has unlimited computing power, even if she knows exactly how the protocol works, she cannot intercept the message without being detected. Quantum mechanics itself protects the communication. It's already being used in practice. Banks, governments, and research institutions use quantum key distribution to secure sensitive communications. The keys are guaranteed secure by the structure of reality itself, not by the assumed difficulty of mathematical problems. There's something deeply satisfying about this. We're not outsmarting potential adversaries. We're enlisting the universe as a partner. We're using nature's own rules, the impossibility of copying quantum states, the unavoidable disturbance of measurement, to protect our secrets. Reality becomes our encryption algorithm, more reliable than any code humans could devise. The double-slit experiment already showed us that observation changes quantum behavior. Particles act like waves when unobserved, like particles when observed. But the quantum eraser experiment takes this strangeness one step further. It suggests you can retroactively change whether a particle behaved as a wave or particle in the past. Here's the setup. Send photons through a double-slit apparatus, but add detectors that mark which slit each photon passes through. Now you get two strips on the screen, no interference, because the which path information destroys the wave-like behavior. The photon, knowing it's being watched, picks one slit and acts like a particle. But then add one more element, a device that erases the which path information after the photon has already passed through the slits, but before it hits the screen. Maybe the device scrambles the detector readings, or entangles them with other particles in a way that makes the original information irretrievable. The point is, by the time the photon reaches the screen, no one, not even in principle, can know which slit it went through. And when you do this, the interference pattern comes back. The photon behaves as if it went through both slits, even though there was a moment when which path information existed. Erasing that information retroactively restores the wave behavior. It gets stranger. You can delay the erasure until after the photon hits the screen. The photon has already landed, already left its mark. But depending on whether you erase the which path information or keep it, a choice you make later, the pattern that emerges from many photons will either show interference or not. This seems to violate causality. How can a choice made now affect what happened in the past? But it's important to understand, you don't see the effect until you correlate results. The overall pattern on the screen looks random regardless. Only when you sort the photon hits based on what you later did with the which path information, erased it or kept it. Do you see interference or no interference in the subgroups? So no information travels backward in time. You can't send messages to the past. But the interpretation is still unsettling. It suggests that whether a photon really went through both slits or just one isn't determined until the entire experimental context is complete, including measurements that happen after the photon's journey is over. Maybe the lesson is that quantum events don't have fixed, context-independent histories. The past at the quantum level is somewhat fluid, not changeable in a way that creates paradoxes, but undetermined until all relevant measurements are complete. The photon's path becomes definite only in retrospect, only when the full story has been told. It's as if reality is waiting to see how the story ends before deciding what happened in the middle, as if the universe keeps its options open until the last possible moment, refusing to commit to a single narrative until forced to by the complete context of observation. Every electronic device you own, every computer, phone, LED light, solar panel, exists because quantum mechanics explains why some materials conduct electricity and others don't. It's a story about how electrons fill energy levels and it reveals something beautiful about how quantum rules create diversity in matter. In a conductor like copper, the electrons in the outermost orbitals aren't bound tightly to individual atoms. Instead, they form what's called a conduction band, a sea of electrons that can move freely through the material. Apply a voltage, and these electrons flow easily. That's electric current. The quantum structure of copper's electron orbitals makes this possible. In an insulator like rubber or glass, electrons are tightly bound to atoms, occupying energy levels well below the conduction band. There's a large energy gap, called the band gap, between the highest filled level and the lowest empty level where electrons could move freely. Electrons can't jump that gap at room temperature, so they stay put. No flow, no current. Semiconductors like silicon sit beautifully in between. They have a band gap, but it's smaller. Small enough that some electrons can jump across it, especially if you add a bit of energy, heat, light, or voltage. Or you can dope the material, adding tiny amounts of other elements that either donate extra electrons or create holes where electrons are missing. Electrons can jump into those holes, which makes the holes appear to move in the opposite direction. This is how transistors work. By carefully controlling the doping and applying voltages, you can create regions where current flows and regions where it doesn't. You can make switches, billions of them on a single chip, turning on and off billions of times per second, processing information at speeds our ancestors couldn't have imagined. All of this, conductivity, insulation, semiconduction, emerges from quantum mechanics, from the Pauli exclusion principle, which determines how electrons fill energy levels, from band theory, which describes how individual atomic orbitals merge into continuous bands in solids, from quantum tunneling, which lets electrons cross barriers they classically couldn't. There's something almost miraculous about it. By understanding quantum rules, we learn to manipulate materials at the atomic level, to engineer their properties, to create substances that nature never made, semiconductors with precisely controlled characteristics, optimized for specific purposes. We turned sand, silicon dioxide, into thinking machines. We harnessed quantum mechanics to build the information age, and every time you tap a screen, send a message, search for information, or watch a video, you're relying on countless electrons making quantum jumps, tunneling through barriers, filling energy bands in ways that classical physics said should be impossible. The device in your hand is a quantum machine, billions of quantum events happening every second, all orchestrated by our understanding of how electrons behave in solids. At temperatures just billionths of a degree above absolute zero, something extraordinary happens. Thousands of atoms can collapse into the same quantum state and behave as one giant atom. It's called a Bose-Einstein condensate, and it's one of the most exotic states of matter ever created. Here's the background. Particles come in two types: fermions, like electrons, which obey the Pauli exclusion principle and refuse to share quantum states, and bosons, like photons, which have no such restriction and can pile into the same state as much as they want. At normal temperatures, even bosonic atoms act independently. They zip around with thermal energy, each following its own path, behaving like tiny classical billiard balls, but cool them down, and I mean really cool them, to within a millionth of a degree of absolute zero, and something changes. Their quantum wave functions, which describe the probability clouds of where each atom might be, start to spread out. And when they spread out enough, they overlap. And when they overlap, and the atoms are bosons. They don't just touch, they merge. Thousands of atoms, all in the same quantum state, their wave functions perfectly synchronized, behaving not as a collection of individuals, but as a single quantum entity. It's like a dance floor where everyone is moving separately, and then the temperature drops and suddenly everyone is moving in perfect unison. Yeah, not because they're following each other, but because they've become one dancer. Bose-Einstein condensates have bizarre properties. They flow without friction, superfluidity, because any obstacle would require individual atoms to scatter, but there are no individual atoms anymore, just one coherent quantum state that can't be disrupted in that way. They can exhibit quantum interference on macroscopic scales, showing wave-like behavior for clouds of atoms visible to the naked eye. They're also incredibly fragile. Any warmth, any stray photon, any vibration can break the spell, jarring atoms out of the collective state. Condensates can only exist in the most isolated, controlled laboratory environments, held in magnetic traps, cooled by lasers, shielded from any disturbance. Einstein predicted these condensates in 1924, and based on earlier work by Indian physicist Satyendra Nath Bose. But it took until 1995 for technology to advance enough to actually create one. When physicists finally succeeded, they essentially made a new form of matter, one that had never existed anywhere in the universe, except perhaps in the first moments after the Big Bang. There's something poetic about Bose-Einstein condensates. They represent the ultimate quantum collectivity. Individual identities completely dissolved to a greater whole. No atom is separate, distinguishable, or independent. They're all one, sharing a single existence, moving as one entity. It's the opposite of the Pauli exclusion principle's enforced separateness. It's fusion instead of distinction, unity instead of isolation. Perhaps it's a reminder that reality permits both modes of being. The fierce individuality of fermions and the collective unity of bosons, separation and merger, distinction and dissolution, and both are quantum, both fundamental, both woven into the fabric of how matter can exist. Despite the name, quantum teleportation isn't about beaming objects from one place to another. Nothing physical travels, no atoms are transported. Instead, quantum teleportation is about transferring information, specifically the quantum state of a particle, from one location to another, without that information ever travelling through the space in between. Here's how it works. Start with two entangled particles. Call them A and B. Give particle A to Alice and particle B to Bob. They can be separated by any distance. Now, an Alice has a third particle, call it C, whose quantum state she wants to send to Bob. She doesn't know what state C is in. If she measured it, the state would collapse. But she wants Bob's particle to end up in exactly the same state that C is currently in. Alice performs a special measurement on particles A and C together, a measurement that entangles them and gives her some classical information. 2 bits, 4 possible outcomes. Because A and C are now entangled, and A was previously entangled with B, particle C's state has been transferred to the AB entangled system, but it's scrambled, encrypted by the randomness of Alice's measurement. Alice sends the 2 classical bits to Bob, by phone, email, carrier, pigeon, any normal channel. Bob receives these bits, and, based on which of the 4 outcomes Alice got, performs a corresponding operation on his particle B, rotate it this way or that, flip it or not depending on the message. And when he's done, Particle B is now in exactly the state that particle C was in originally. The quantum information has teleported from C to B. Particle C itself has been destroyed in the process. Its original state collapsed during Alice's measurement. The no-cloning theorem guarantees you can't copy unknown quantum states, only move them. This has been demonstrated experimentally with photons, atoms, and even small groups of particles. It's not science fiction. It's real quantum technology, potentially useful for quantum computing and ultra-secure communication. But notice, it required both quantum entanglement and classical communication. The entanglement provided the quantum channel, but Bob couldn't complete the teleportation without receiving classical information from Alice. So nothing travels faster than light. Causality is preserved. But quantum information can be transferred perfectly, with absolute fidelity, from one particle to another that has never interacted with the first. It's as if the universe allows perfect copying of states, but only if the original is destroyed in the process. Only if information moves rather than multiplies. As if reality has a conservation law for quantum information, it can flow, transfer, relocate, but never duplicate. Perhaps there's a deeper principle here about identity and information. In quantum mechanics, a particle's state is its identity. If you perfectly transfer that state to another particle, have you moved the first particle or created a copy? The universe's answer seems to be, you've moved it, because the original ceased to exist. Identity can teleport, but only if it's singular, only if there's always just one instance of any given quantum state. In 2012, physicists at CERN announced the discovery of the Higgs boson, a particle that had been predicted theoretically in the 1960s but never observed. The announcement made headlines worldwide, and for good reason. The Higgs boson explains why particles have mass at all. Here's the puzzle it solves. According to the Standard Model, particles like electrons and quarks should be massless, zipping around at light speed like photons. But they're not. They have mass. They move slower than light. They resist acceleration. They pull on each other through gravity. Why? The answer involves a field, the Higgs field, that permeates all of space. It's always there, everywhere, at a constant non-zero value. And particles acquire mass by interacting with this field. The more strongly a particle couples to the Higgs field, the more mass it has. Electrons interact weakly, so they're light. Top quarks interact strongly, so they're heavy. Photons don't interact at all, so they remain massless. You can think of it like moving through a room crowded with people. Some objects, like a celebrity, interact strongly with the crowd, constantly getting stopped and slowed down. That's like a massive particle interacting with the Higgs field. Other objects, like an unknown person, move through easily, barely interacting. That's like a massless particle. The Higgs boson is an excitation of the Higgs field, a quantum ripple. Just as photons are ripples in the electromagnetic field, finding the Higgs boson was important because it confirmed that the Higgs field actually exists. The field gives mass to particles. The boson is the evidence that the field is real. Without the Higgs field, electrons and quarks would be massless. They couldn't slow down enough to form atoms. Protons and neutrons wouldn't exist. Chemistry would be impossible. Stars wouldn't form. The universe would be very different. Perhaps just photons and other massless particles flying through space forever, never combining into anything complex. But the Higgs field does exist. It fills space with a subtle presence, giving mass to particles that interact with it, allowing matter to be massive and thus allowing structure, chemistry, planets, life. Every atom in your body has mass because of the Higgs field. Every step you take, every breath, every heartbeat involves mass that exists only because of this field. And yet, we barely understand it. Why does the Higgs field have the value it does? Why do different particles couple to it with the specific strengths they have? Why is there a Higgs field at all? These remain mysteries. The discovery of the Higgs boson answered one question. Yes, the field exists, but opened many more. Perhaps that's always how science works. Each answer reveals new questions, deeper mysteries. We explained why particles have mass, but not why the Higgs field exists, or why it has its particular properties. We've descended one level, but the basement turns out to have a staircase leading further down, and maybe that's okay. Maybe the joy is in the descent itself, in the questions as much as the answers, in the ongoing conversation with reality that never quite reaches a final word. For thousands of years, philosophers and scientists believed the universe was fundamentally deterministic. If you knew the position and velocity of every particle, you could, in principle, predict the future perfectly and retrodict the past completely. The universe was a vast clockwork mechanism, and randomness was just a mask for ignorance. Quantum mechanics shattered that worldview. It revealed that some things are genuinely, irreducibly random. Not random because we lack information, but random because the universe itself hasn't decided yet. When an electron in a superposition of spin up and spin down is measured, it randomly becomes one or the other. The probabilities are precise, maybe 50-50, maybe 70-30, depending on the quantum state, but the specific outcome is unpredictable. Not unpredictable in practice, but unpredictable in principle. There is no hidden variable determining the result. The electron genuinely doesn't have a definite spin until measured. The measurement creates the outcome, not reveals it. This isn't a philosophical stance or an interpretation. Bell's theorem, which we discussed earlier, proved that no local hidden variable theory can reproduce quantum predictions. Experiments confirmed the predictions. The randomness is real. It's woven into the structure of reality at the most fundamental level. Think about what this means. The universe, in its deepest layer, makes choices. Moment by moment, countless quantum measurements are occurring, particles decaying, where photons being absorbed, electrons jumping between orbitals, and each one involves a genuinely random outcome. The future isn't written, it's being improvised, constantly, in trillions upon trillions of quantum decisions happening every instant. This doesn't mean chaos. The probabilities are lawful, predictable, precise. Quantum mechanics tells you exactly how likely each outcome is, but within those probabilities there's freedom, genuine openness, true contingency. Reality rolls the dice, and the universe we experience emerges from the accumulated results of those rolls. Some people find this disturbing. Einstein certainly did. He wanted a universe that was orderly, determined, knowable, one where everything happened for a reason, where nothing was left to chance. God does not play dice, he insisted. We're hoping quantum randomness would eventually be explained away by a deeper theory. But maybe randomness isn't a flaw in the universe's design. Maybe it's a feature. Maybe a cosmos where the future is open, where genuine novelty can emerge, where outcomes aren't predetermined, is richer and more interesting than a mechanical clockwork running down predetermined tracks. Perhaps quantum randomness is what allows the universe to be creative, to explore possibilities, to generate outcomes that weren't simply encoded in initial conditions. And if the universe can be creative at the quantum level, perhaps that same creativity scales up through chemistry, through biology, through consciousness, to allow genuine choice, genuine newness, genuine freedom at every level of existence. Empty space isn't empty. We've mentioned this before, but let's look at one of its most striking demonstrations, the Casimir effect, where two metal plates placed very close together in a vacuum experience an attractive force pulling them together, even though there's nothing between them. Nothing, that is, except the quantum vacuum. According to quantum field theory, the vacuum is filled with virtual particles, particle-antiparticle pairs that pop into existence, borrow energy from the uncertainty principle, and annihilate back into nothing in fractions of a second. These virtual particles exist everywhere, constantly, as a kind of quantum foam underlying reality. Now place two metal plates very close together, just nanometers apart. The metal plates restrict which virtual particles can exist between them. Virtual photons come in all wavelengths. Some, but only photons with wavelengths that fit exactly between the plates, like standing waves in a musical instrument, can exist in that narrow gap. Outside the plates, all wavelengths are allowed. This creates an imbalance. There are more virtual photons pushing on the outside of the plates than pushing from between them. The result, a net force pushing the plates together. Not a huge force. At nanometer separations, it's equivalent to about 1 atmosphere of pressure, but it's real, measurable, and purely quantum mechanical. The Casimir effect has been measured many times with increasing precision. It's not speculation or mathematical abstraction. It's a genuine physical force arising from quantum fluctuations in supposedly empty space. Think about the philosophical implications. The vacuum isn't a peaceful nothing. It's a roiling sea of activity happening at scales and speeds we can't directly perceive. Particles winking in and out of existence, energy borrowing and repaying itself, fields vibrating with zero-point motion that can never be stilled. Even if you removed every atom, every photon, every particle from a region of space, even if you cooled it to absolute zero, it wouldn't be empty. It would still contain quantum fields, still undergo fluctuations, still exert forces. True nothingness, it seems, is impossible. The universe doesn't permit it. Perhaps that's comforting. It means the universe is never truly dead, never completely still. Even in the darkest, coldest, most isolated reaches of space, quantum activity persists. Reality hums with a baseline creativity, an irreducible liveliness that cannot be switched off. And from our perspective, the Casimir effect is a window into that hidden activity. By placing two plates close together, we're essentially eavesdropping on the quantum vacuum, making the invisible visible, allowing the ghost-like virtual particles to leave measurable traces. We're catching reality in the act of its constant self-creation. We've touched on this before, but it's worth revisiting. The Pauli exclusion principle is the reason matter takes up space, the reason you're a definite size and shape rather than a diffuse cloud or a point. The principle, stated simply, is this: no two identical fermions can occupy the same quantum state. Electrons are fermions, so are protons, neutrons, and quarks. And this prohibition, this quantum no trespassing sign, is absolute. In an atom, electrons fill orbitals from lowest energy upward. The first electron goes in the lowest orbital. The second electron can join it, but only if it has opposite spin, making it a different quantum state. The third electron has to go to the next orbital up because the first orbital is now full, and so on, building up the electron shells that determine chemical properties. This is why the periodic table exists, why elements have the properties they do, why chemistry happens. The Pauli exclusion principle forces electrons into higher orbitals, creating structure, diversity, the capacity for different elements to behave differently. But it goes beyond chemistry. When you push on a wall, you're feeling the Pauli exclusion principle in action. The electron clouds in your hand and the wall are both filled with electrons, and those electrons refuse to overlap. They can't occupy the same states, so they repel, not just through electromagnetic forces, but through this quantum prohibition. If the exclusion principle didn't exist, all electrons in an atom could collapse into the lowest orbital. Atoms would be far smaller and denser. Matter would pack together much more tightly. You could probably compress your body into a grain of sand. The universe would be very different, cramped, dense, structureless. But the exclusion principle does exist, and it enforces separation. It draws boundaries. It insists that fermions maintain their individuality, their distinctness, their refusal to merge with others. It's what makes you a separate entity from the chair you're sitting on, from the air around you, from other people. There's something almost profound about that. Not your physical separateness, the fact that you're here and not there, the fact that you have boundaries, ultimately traces back to a quantum rule about electrons refusing to share states. Identity, at the most basic level, is quantum mechanical. You are separate because the universe has laws that enforce separation. And yet remember, bosons don't obey the exclusion principle. Photons can pile into the same state. So can certain atoms under the right conditions. The universe permits both modes. Fierce individuality for fermions, collective unity for bosons. Perhaps both are necessary. Perhaps reality needs both distinction and merger, both separation and connection, to have the richness it displays. Quantum dots are tiny crystals, semiconductors just a few nanometers across, containing anywhere from a few hundred to a few thousand atoms. They're so small that electrons inside them are confined to an incredibly tiny space, and when you confine electrons that tightly, quantum effects take over completely. In a normal bulk semiconductor, electrons can move relatively freely through the material. They occupy bands of energy levels that are almost continuous. But in a quantum dot, the confinement is so extreme that electrons can only occupy specific, discrete energy levels, like electrons in atoms. But in this case, the atom is a tiny crystal. And here's the beautiful part. The size of the quantum dot determines the spacing between energy levels. Make the dot smaller, and you squeeze the electrons more tightly, raising their energy levels and increasing the gaps between them. Make it larger, and the levels come closer together. This means you can tune the color of light a quantum dot emits just by changing its size. Larger dots emit red light, longer wavelength, lower energy. Smaller dots emit blue light, shorter wavelength, higher energy. In between, you get every color of the rainbow. This isn't done by adding dyes or pigments. It's purely quantum mechanical. The size of the confinement determines the electron energy levels, which determines which photons can be absorbed or emitted, which determines the color. Quantum dots are now used in high-end television displays, producing incredibly vivid, pure colors because the emission wavelengths are so precisely controlled. They're used in biological imaging, as tiny fluorescent markers that can be attached to proteins or cells. They're being explored for solar cells, LEDs, quantum computing, and medical diagnostics. But beyond the applications, quantum dots are beautiful demonstrations of quantum confinement. They show that you can engineer quantum properties by controlling structure at the nanoscale. You can design the energy levels, tune the behavior, create materials with properties that nature never made. It's as if we've learned to speak the universe's language, to whisper to atoms in their own tongue, asking them to behave in specific ways. And they listen. They respond. Electrons confined in tiny crystals emit exactly the colours we designed them to emit, following quantum rules we've only understood for 100 years. Perhaps this is what technology ultimately is, learning reality's grammar and using it to construct new sentences, new forms, new possibilities. We didn't invent quantum confinement. We discovered it, understood it, and then learned to harness it. And in doing so, we became collaborators with the quantum world, partners in creating things that have never existed before. We've mentioned it in passing several times, but let's face it directly. Quantum mechanics doesn't actually tell us what measurement is or why it causes wave function collapse. This is called the measurement problem, and despite a century of quantum theory, it remains unsolved. Here's the issue. Before measurement, a quantum system exists in superposition, a combination of multiple possible states, all coexisting. An electron is both spin up and spin down. A photon is both here and there. The math describes this superposition perfectly, and it evolves smoothly according to Schrödinger's equation. But when you measure the system, something changes. The superposition collapses, where suddenly the electron is definitely spin up or definitely spin down. The photon is in one location. All the other possibilities vanish, and you're left with one concrete outcome. The problem, quantum mechanics doesn't explain this collapse. Schrödinger's equation describes smooth deterministic evolution of the wave function. Collapse is abrupt, random, and seems to violate that equation. It's like the theory has two different sets of rules. One for when nobody's looking, smooth evolution, and another for when someone measures, abrupt collapse. What counts as a measurement? Does it require a conscious observer, a detector, any interaction with a large object? Nobody knows. The math works perfectly for predicting outcomes, but it's silent on what actually happens during measurement. Different interpretations offer different answers. The Copenhagen interpretation says collapse is fundamental but doesn't explain it. Measurement just works differently, and that's that. The Many Worlds interpretation says there's no collapse at all. Every possibility happens, creating parallel universes for each outcome. Objective collapse theories suggest the wave function spontaneously collapses when systems reach a certain size or mass. Pilot wave theories reintroduce determinism through hidden variables that guide particles. None of these interpretations has been proven. All of them reproduce the same experimental predictions, because they're all based on the same underlying math. The choice between them comes down to philosophy, aesthetics, intuition, not experimental evidence. Perhaps the measurement problem is telling us that quantum mechanics, for all its success, is incomplete. Not wrong, but not the final word. Perhaps there's a deeper theory that will explain measurement naturally, the way general relativity explained gravity more deeply than Newton did. Or perhaps measurement is genuinely fundamental, an irreducible aspect of reality that can't be reduced to anything simpler. Perhaps the universe really does have two modes of being: potential, superposition, and actual, collapsed, and measurement is the bridge between them. Maybe we're asking the wrong question. Maybe what is measurement is like asking what is time, or what is existence? A question so fundamental that it doesn't have an answer within the framework we're using. Maybe measurement is one of the basic elements of reality, like space or energy, that can't be defined in terms of anything else. For now, the measurement problem remains an open question at the heart of our most successful physical theory. A reminder that however much we know, however precisely we can predict, there are still deep mysteries about what reality is and how it works, and perhaps that's appropriate. Perhaps the universe should have secrets that resist our attempts to fully understand them. Perhaps some mysteries should remain, keeping us humble, keeping us curious, keeping us aware that for all our knowledge, we're still just beginning to comprehend the strange and beautiful cosmos we inhabit. Here's one of the deepest puzzles in all of physics, sitting at the intersection of quantum mechanics and cosmology. The vacuum of empty space should have enormous energy density, so enormous it should tear the universe apart, but it doesn't. Let me explain. We know from quantum mechanics that the vacuum isn't empty. It's filled with quantum fields undergoing zero-point fluctuations, virtual particles popping in and out of existence, energy borrowed and repaid on timescales so short we can barely measure them. All this activity should contribute to the vacuum's energy density. When physicists calculate how much energy the quantum vacuum should have, they get an absurdly large number. Depending on how you do the calculation, it comes out to something like 10 to the power of 120 times larger than what we observe. That's one followed by 120 zeros. It's not just wrong, it's spectacularly, catastrophically wrong. It might be the worst prediction in the history of physics. Here's why it matters. Vacuum energy affects the expansion of the universe. Einstein's general relativity includes a term called the cosmological constant, which describes the energy density of empty space. If that constant were as large as quantum mechanics predicts, the universe would be expanding so violently that galaxies couldn't form, stars couldn't ignite, and we wouldn't exist. But we do exist. The universe is expanding, but at a measured, sedate pace, accelerating, yes, thanks to dark energy, but nowhere near the catastrophic rate that quantum vacuum energy would produce. Observations show the cosmological constant is tiny. Not zero, but something like 10 to the power of minus 120 in the units physicists use. Extraordinarily small. So quantum mechanics predicts one value, observations show another, and they disagree by 120 orders of magnitude. Something is deeply wrong with our understanding. Either quantum field theory is missing something crucial, or general relativity is incomplete, or both need to be modified when combined. Many physicists have tried to solve this problem. Maybe there's a symmetry in nature that forces the vacuum energy to be exactly zero, and the tiny value we observe is a separate phenomenon. Maybe different contributions to vacuum energy, positive and negative, cancel out almost perfectly, leaving just a tiny remainder. Maybe we live in a multiverse where the cosmological constant varies between universes, and we happen to be in one of the rare universes where it's small enough to allow life. None of these solutions is fully satisfying. The problem remains open, gnawing at the foundations of physics. It suggests that our two greatest theories, quantum mechanics and general relativity, don't fit together properly. They work brilliantly in their own domains, but at the boundary where both should apply, something breaks down. Perhaps the cosmological constant problem is nature's way of telling us we're missing something profound, some new principle, some deeper understanding that will make the puzzle dissolve. Or perhaps it's teaching us humility, reminding us that the universe doesn't owe us consistency, doesn't promise that our theories will mesh seamlessly. Reality is under no obligation to make sense to creatures who've only been doing physics for a few centuries. Still, it's worth pondering as you drift towards sleep. The universe exists in a delicate balance, its expansion neither too fast nor too slow, its vacuum energy neither crushing nor negligible, and we don't know why. We can describe what is, but not explain why it is rather than something catastrophically different. Maybe that's enough for now. Maybe the mystery can wait while you rest. We talked about the Higgs boson earlier, but let's think about the Higgs field from a different angle. Every particle in your body that has mass, every electron, every quark, has that mass because it's constantly interacting with an invisible field that fills all of space. You are, in a very real sense, shaped by the Higgs field. If the field didn't exist, or if it had a different strength, the particles that make up your atoms would have different masses. Chemistry would work differently. Stars would burn differently. The entire history of the universe would have unfolded along a different path. The Higgs field has a specific value, about 246 giga-electron-volts in the units physicists use. This isn't zero, like most fields in empty space. The electromagnetic field, when there's no charge around, sits at 0. The electron field, when there are no electrons, sits at 0. But the Higgs field, even in a perfect vacuum, has a constant non-zero value permeating everything. Why that particular value? Nobody knows. It's one of the fundamental parameters of the Standard Model, a number we measure but can't derive from deeper principles. If it were much smaller, electrons and quarks would be nearly massless, and atoms wouldn't hold together. If it were much larger, particles would be so heavy that the universe would be very different, perhaps unable to form complex structures. It's tempting to think of the Higgs field as a kind of cosmic syrup. You're making particles sticky and slowing them down, giving them inertia and mass. But that's not quite right. The field doesn't slow particles, it couples to them, and that coupling manifests as mass. Particles that don't couple to the Higgs field, like photons, remain massless and travel at light speed. Particles that couple strongly become massive and travel slower. There's something almost tender about this. The universe doesn't just contain matter, it supports matter, gives it mass, allows it to have the properties needed to form stable structures. The Higgs field is like a foundation, invisible but necessary, holding up everything that has weight and substance. And you're part of that. Every breath you take involves particles whose mass comes from the Higgs field. Every heartbeat, every thought, every movement relies on massive particles behaving the way they do because of their interaction with this omnipresent field. You're not separate from the Higgs field, you're immersed in it, shaped by it, made possible by it. Perhaps there's something comforting about knowing that. You're not alone, floating in empty space. You're supported, surrounded, interpenetrated by fields that give particles their properties. The universe is more intimate than it first appears, not a collection of separate objects in a void, but a web of fields and interactions, everything connected, everything influenced by invisible presences that fill every point in space. When you flip a coin, it lands heads or tails, and before you look, you'd say there's a 50% probability of each outcome, but that probability is really just ignorance. The coin actually is heads or tails. Air current, spin rate, initial conditions all determine the result. If you knew everything, you could predict it perfectly. Probability in this case is just a measure of what you don't know. Quantum probability is different, fundamentally different. When an electron in a superposition is measured, the probabilities aren't describing your ignorance, they're describing reality itself. The electron genuinely doesn't have a definite state before measurement. It's not secretly spin up and you just don't know yet. It's actually both and neither until the measurement forces it to become one or the other. This difference is subtle but profound. Classical probability is epistemic. It's about knowledge, about what you know or don't know. Quantum probability is ontic. It's about what exists, about reality itself being undetermined. And the probabilities in quantum mechanics have a strange mathematical structure. They're not just numbers between 0 and 1, like classical probabilities. They're complex numbers that involve both real and imaginary parts, and they combine through interference in ways that classical probabilities never do. When two possibilities exist in superposition, their probability amplitudes can add or subtract, reinforcing or cancelling each other. This is what creates interference patterns in the double-slit experiment. Classical probabilities can only add. If something can happen two ways, you add the probabilities of each way. But quantum probability amplitudes can subtract, can cancel out, can interfere destructively to make outcomes less likely than if only one path existed. This is mathematically beautiful and conceptually strange. It means quantum mechanics isn't just classical mechanics with randomness added. It's a different kind of theory entirely, one where probabilities have internal structure and can interact with each other before collapsing into definite outcomes. And yet, when you actually measure something, you get normal probabilities, non-negative numbers that add up to 1, just like in classical probability. The complex amplitudes become real probabilities at the moment of measurement. The interference effects collapse into ordinary likelihood. Perhaps what this is telling us is that reality has layers. There's the layer we experience, definite outcomes, concrete events, classical probability describing our uncertainty about facts. And there's a deeper layer, quantum amplitudes, superpositions, a richer mathematical structure that underlies the classical surface. Measurement is the interface between these layers, the moment when depth collapses into surface, when quantum potential becomes classical actuality. Or perhaps measurement is when we, as observers, enter the system, when the quantum world makes contact with our classical scale consciousness and translates itself into terms we can comprehend. The complex amplitudes are reality in itself. The real probabilities are reality for us, and the mystery is in how one becomes the other, how the deeper truth becomes the surface we experience. There's a common misunderstanding about quantum mechanics that's worth clearing up as you drift towards sleep. The observer effect doesn't mean consciousness creates reality, or that minds have special quantum powers. When physicists talk about observation or measurement, they don't mean a person looking at something. They mean any interaction that extracts information from a quantum system and records it in the environment. A detector counts, a photographic plate counts, even another atom interacting in the right way counts. You don't need a conscious mind. You don't need a human observer. The universe was performing measurements for billions of years before any consciousness existed. Stars were absorbing and emitting photons, collapsing quantum states, creating definite outcomes, all without anyone watching. The confusion arises because early quantum mechanics was developed with laboratory experiments in mind, where human experimenters were indeed observing results. And some of the founders, particularly Eugene Wigner, speculated that consciousness might play a role in wave function collapse, but that was speculation, not settled science. And most physicists today don't think consciousness is necessary for measurement. What matters is decoherence, the process where a quantum system becomes entangled with its environment in irreversible ways. When a photon interacts with a detector, it creates a cascade of effects: electrons moving, atoms being ionized, macroscopic needle positions changing, and all these changes get entangled with the environment. The quantum superposition doesn't collapse because someone looked. It collapses because information about the outcome has spread into the environment in ways that can't be undone. You can think of it like footprints in snow. Once you've left tracks, vajamd, the snow knows you walked there, even if no person sees the tracks. The environment records the outcome, and that recording is what constitutes measurement. Consciousness isn't needed, just interaction, just information transfer, just irreversible entanglement with the wider world. This doesn't make quantum mechanics less mysterious, it just moves the mystery. Instead of, why does consciousness collapse wave functions, we ask, why does decoherence produce definite outcomes? What makes some interactions count as measurements while others don't? At what point does a quantum superposition become a classical fact? These remain open questions, but they're not about consciousness having magical powers. They're about the boundary between quantum and classical, about how macroscopic definiteness emerges from microscopic superposition, about the transition from potential to actual. Perhaps it's a relief in a way. You don't need to worry that your thoughts are collapsing wave functions, that your observations are creating reality. The universe was doing just fine before you arrived, and it'll continue after you're gone. Quantum mechanics is strange, but it's not solipsistic. Reality exists independently of minds, even if minds are part of reality and participate in its unfolding. So rest easy. The quantum world doesn't need you to sustain it. You're free to sleep, to let consciousness fade, and the universe will keep on with its quantum business, collapsing wave functions, measuring itself, creating the classical world moment by moment, all without requiring your attention. We've mentioned several times that quantum mechanics and general relativity, our two foundational theories, don't fit together. Relativity describes gravity beautifully at large scales. Quantum mechanics describes matter and energy beautifully at small scales. But when you try to combine them to create a quantum theory of gravity, the math breaks down in disturbing ways. The equations produce infinities that can't be removed. Predictions become nonsensical. The theory can't tell you what happens at the center of a black hole or in the first moments after the Big Bang. Places where gravity is strong and quantum effects are unavoidable. We need a theory that combines both, and we don't have one. String theory is the most developed attempt to solve this problem. Instead of treating particles as point-like objects, the string theory proposes they're tiny vibrating strings, loops of energy oscillating in different patterns. An electron is a string vibrating one way, a quark is a string vibrating another way. Different vibrations correspond to different particles, and one of those vibrations, one particular pattern of oscillation, corresponds to the graviton, the hypothetical particle that carries gravitational force. String theory naturally includes gravity. It's a quantum theory that contains general relativity as an approximation. If it's correct, it would unite all forces and all particles into one mathematical framework. But there's a catch. Actually, several catches. String theory requires extra dimensions, not just the 3 of space and 1 of time we experience, but 6 or 7 additional dimensions curled up so small we've never detected them. The theory has no unique solution. There are something like 10 to the power of 500 different possible configurations, each describing a different possible universe. And most crucially, string theory has made no predictions we can test experimentally. The energy scales where it matters are far beyond what any particle accelerator can reach. So is string theory right? We don't know. It's mathematically beautiful, elegantly structured, and completely unproven. It might be the true theory of everything, or it might be an elaborate mathematical fiction with no connection to reality. Loop quantum gravity is an alternative approach. It keeps space-time as fundamental, but makes it granular, quantized, built from discrete loops rather than being smooth and continuous. It too has mathematical promise and no experimental confirmation. Yeah, perhaps the search for quantum gravity is teaching us patience. For 100 years we've lived with the tension between our two great theories, unable to reconcile them. Maybe that's okay. Maybe the universe is complex enough that understanding it requires more than one human lifetime, more than one generation of physicists, more time than we've had so far. Or perhaps quantum gravity will remain forever beyond our reach, not because we're not clever enough, but because the universe doesn't give us access to the conditions where it matters. Black hole centers and Big Bang moments are hidden behind horizons, inaccessible to experiment, knowable only through mathematics and speculation. Still, the search continues. Physicists keep building theories, keep probing mathematical possibilities. I keep hoping that somewhere in the equations there's a clue, a hint of how to marry quantum mechanics and gravity, how to describe reality at its deepest level, and maybe someday they'll succeed. Maybe someone not yet born will see the answer that's eluded everyone so far. Or maybe the mystery will persist, remaining just out of reach, forever inviting us deeper while never quite revealing its final secrets. Let's return to something fundamental. Something that distinguishes quantum mechanics from every physical theory that came before it. Probability isn't an add-on or an approximation. It's woven into the core of the theory itself. In classical physics, you use probability when you don't know all the details. The molecules in a gas are all following deterministic laws, but there are too many to track. And so you use statistical mechanics. Probability is a practical tool for dealing with complexity. But in principle, everything is determined. The probabilities reflect your ignorance, not the universe's uncertainty. Quantum mechanics is different. The wave function, the mathematical object that describes a quantum system, doesn't tell you what will happen. It tells you the probabilities of different outcomes. And this isn't because we're missing information. It's because the universe itself is probabilistic at this level. Max Born figured this out in 1926. Schrödinger had written his wave equation, and everyone was trying to understand what the wave function meant physically. Born proposed that the wave function's amplitude squared gives the probability of finding a particle at different locations, not the certainty, the probability. This interpretation won Born a Nobel Prize, and it's been confirmed by every quantum experiment ever performed. So when you calculate in quantum mechanics, you're not predicting what will happen. You're calculating likelihoods, how often each outcome will occur if you repeat the experiment many times. Any individual result is uncertain. Only the statistical pattern is predictable. This represents a profound shift in what physics is trying to do. Newton's laws predicted exactly where planets would be. Maxwell's equations predicted exactly how electromagnetic fields would evolve. Even Einstein's relativity is deterministic. Given initial conditions, the future unfolds uniquely. But quantum mechanics says, given initial conditions, multiple futures are possible, each with a specific probability. The best you can do is describe the odds. The universe plays games of chance, and physics has become the study of how those games work, what the rules are, what probabilities apply in different situations. Some people find this philosophically troubling. If physics can't predict definite outcomes, is it really describing reality? Or just our knowledge of reality? But perhaps this is too demanding. Perhaps asking for certainty about the future is asking too much. Perhaps the universe is under no obligation to be deterministic just because we'd prefer it that way. And there's a beauty to probability-based physics. It means the universe is open, not closed. The future is genuinely undecided, genuinely contingent on outcomes that haven't happened yet. Each quantum measurement is a moment of creation, bringing one possibility into actuality while others fade away. Reality is being written moment by moment through countless quantum events, none of them predetermined. Maybe that's not a flaw in the universe's design. Maybe it's what makes the cosmos interesting, what allows for surprise, for novelty, for genuine creativity at every scale. A purely deterministic universe would be a machine running down, its entire history implicit in its beginning. But a probabilistic universe can surprise itself, can generate outcomes not encoded in initial conditions, can be genuinely creative. So rest with this thought: the future is open, not completely. Quantum probabilities constrain what can happen, but within those constraints, there's room for chance, for possibility, for outcomes that aren't yet decided. The universe is improvising moment by moment, and you're part of that ongoing improvisation. Here's something worth clarifying as we near the end of our quantum journey. The double-slit experiment shows that observing which path a particle takes destroys the interference pattern, but observing doesn't mean looking with your eyes. It means any process that extracts which path information and records it in a way that could be read. You could set up detectors at the slits and never look at their output, never check which slit the particle went through. The information exists in the detector's state, but no conscious being accesses it. The interference pattern still disappears. The measurement has happened, even though nobody measured. You could even set up the detector and then destroy it before reading the result. The particle knows the information was recorded, that there was a moment when which path information became accessible, and behaves accordingly. No interference. The universe doesn't care whether you, specifically, learn the outcome. It cares whether the outcome became definite, whether it left a mark, whether it entangled with the environment in irreversible ways. That's what counts as measurement, not consciousness, not observation in the everyday sense, just information transfer, just irreversible entanglement, just the spreading of quantum correlations into the wider world. This is actually good news, philosophically. It means quantum mechanics isn't magical or mystical. It doesn't require minds or consciousness or observers in any special sense. The rules are physical, not psychological. They're about how systems interact, and how information propagates, how quantum states become entangled with classical scale objects. A rock rolling down a hill creates measurements. Photons from the sun interact with Earth's atmosphere, collapsing quantum states, all without any observers. The universe measured itself for billions of years before life evolved. Quantum mechanics was operating long before any consciousness existed to contemplate it. So the observer effect is a misnomer. It should be the interaction effect, or the information effect, or the decoherence effect. But observer effect stuck, perhaps because early experiments involved human observers reading instruments. The name is misleading, but the phenomenon is real. Extracting which path information, whether or not anyone reads it, changes how particles behave. This doesn't make the phenomenon less strange. It's still weird that information matters, that recording an outcome affects behavior, that the universe responds differently to situations where information could in principle be known versus situations where it couldn't. But it removes the mysticism, the idea that human consciousness has special quantum powers. You're part of the universe, not separate from it. Your observations are interactions like any other. You participate in quantum measurements, but so does everything else. Detectors, atoms, rocks, planets, stars. The cosmos is constantly measuring itself, collapsing wave functions, creating definite outcomes through countless interactions. And consciousness is just one kind of interaction among many, with no special status in the quantum world. Perhaps that's humbling. We're not central to quantum mechanics, i.e. not necessary for its operation, but perhaps it's also liberating. You don't have to sustain reality with your attention. The universe handles its own quantum business, and you're free to rest, to sleep, to let go, knowing that reality will persist just fine without your conscious participation. We talked about the Standard Model earlier, the quantum field theory that describes all known particles and forces. It's spectacularly successful, but it's also spectacularly incomplete, and physicists know exactly what it's missing. First, gravity. The Standard Model describes 3 of the 4 fundamental forces: electromagnetic, weak nuclear, and strong nuclear. But gravity isn't included. General relativity handles gravity beautifully, but it's not a quantum theory, and it doesn't integrate with the Standard Model. We have 2 separate frameworks that don't talk to each other. Second, dark matter. Astronomical observations show that galaxies contain much more mass than we can see. Stars orbit faster than visible matter can account for. Galaxy clusters hold together with more gravitational pull than their luminous matter provides. Something invisible, something that doesn't interact with light, makes up about 85% of the matter in the universe. The Standard Model doesn't include any particle that could be dark matter. Third, dark energy. The universe is expanding, and that expansion is accelerating. Something is pushing space apart, overcoming gravity's pull. We call it dark energy, but we have no idea what it is. It makes up about 70% of the universe's total energy. The Standard Model says nothing about it. Fourth, the mass hierarchy. Why do particles have the masses they do? The electron is about 200 times lighter than the muon, which is about 17 times lighter than the tau. Quarks range from almost massless to enormously heavy. The Standard Model measures these masses, but doesn't explain them. They're free parameters, numbers you plug in by hand because the theory doesn't derive them. Fifth, neutrino masses. For decades, the Standard Model assumed neutrinos were massless, but experiments proved they have tiny masses and can oscillate between different types. This requires physics beyond the standard model, new particles, new interactions, new mechanisms we're still piecing together. Sixth, matter-antimatter asymmetry. The Big Bang should have created equal amounts of matter and antimatter, which should have annihilated, leaving only light. But we exist. Matter dominates. The standard model allows for some asymmetry, but not enough to explain the universe we observe. So the standard model, for all its successes, is clearly not the final theory. It's missing gravity, dark matter, dark energy, mass explanations, neutrino physics, and a full account of matter-antimatter imbalance. It's a brilliant, predictive, experimentally confirmed theory that nonetheless covers only about 5% of the universe's content. This might seem discouraging. We've worked so hard and understood so little. But perhaps it's exciting instead. It means there's more to discover. New physics waiting beyond the standard model's edges. Deeper principles, richer structures, explanations for phenomena we currently just measure and catalogue. The standard model is a plateau, not a summit. We've climbed high enough to see vast territories beyond, realms we don't yet understand, and the journey continues. Experiments at particle accelerators, observations of distant galaxies, theoretical explorations of mathematical possibilities. Somewhere in all that effort, answers are waiting, or perhaps better questions, or perhaps mysteries that will invite yet another generation to climb higher still. We mentioned string theory earlier, but let's think about why it's so appealing despite lacking experimental proof. String theory isn't just a theory of quantum gravity, it's potentially a theory of everything, a single mathematical framework that could explain all particles and all forces. In string theory, the fundamental objects aren't point particles but tiny strings, loops of energy vibrating in different patterns. And just as a violin string can vibrate in different modes to produce different notes, these fundamental strings can vibrate in different patterns to produce different particles. One vibration mode gives you an electron, another gives you a photon, yet another gives you a quark. Every particle in the standard model emerges from the same kind of string, just vibrating differently. It's an elegant unification, one fundamental object producing all the diversity we observe, and crucially, one of the vibration modes corresponds to a massless spin 2 particle. That matches the properties of the graviton, the hypothetical particle that would carry gravitational force if gravity were quantized. String theory doesn't just allow gravity, it requires it. Gravity emerges automatically from the mathematics, which is why string theorists find the theory so compelling. But the theory works only in specific numbers of dimensions, 10 or 11 depending on the version. Our universe appears to have 4 dimensions, 3 of space, 1 of time. String theory explains this by suggesting the extra dimensions are curled up incredibly small, so small we've never detected them, perhaps too small to ever detect directly. The way these extra dimensions curl up, their shape, their size, determines the properties of particles and forces in our observable 4 dimensions. Different configurations give different physics, and there are many, many possible configurations, enormous landscape of possible universes, each with different laws. This is both string theory's promise and its problem. The promise. It could explain why our universe has the properties it does, why particles have their particular masses, why forces have their particular strengths. The problem, with so many possibilities, the theory doesn't make unique predictions. It can accommodate almost any observation, which makes it hard to test. For decades, string theorists have searched for predictions that could distinguish their theory from alternatives, but the energy scales where string effects become noticeable are fantastically high, far beyond any conceivable particle accelerator. We might be stuck with indirect evidence, mathematical consistency, and aesthetic appeal rather than direct experimental confirmation. Still, the effort continues. Thousands of physicists work on string theory, exploring its mathematics, searching for testable predictions, hoping that somewhere in the equations there's a clue we can verify. Maybe they'll succeed. Maybe future technologies will allow tests we can't imagine now. Or maybe string theory will remain forever in the realm of elegant speculation, beautiful, consistent, and unproven. Either way, it represents a dream. The dream of a final theory, a single equation from which all of physics flows, a complete understanding of the quantum world and how it gives rise to everything we observe. Perhaps we'll achieve that dream. Or perhaps reality is too rich, too layered, too inexhaustibly complex to ever fit into one framework. Time will tell. The universe has waited billions of years already. It can wait a while longer while we figure things out. We've reached our final quantum fact, and it's fitting that it's about what we still don't understand. After a century of quantum mechanics, after countless experiments, technological applications, Nobel Prizes and breakthroughs, we still debate what the theory means. The math works perfectly. The predictions are flawless. But what it tells us about reality's nature remains genuinely unclear. The Copenhagen interpretation says measurement is fundamental, wave function collapse is real, and asking what happens between measurements is meaningless. Just calculate probabilities and shut up, essentially. The many worlds interpretation says there's no collapse. Every possibility happens, creating parallel universes for each outcome. You measure spin up in this universe. Another version of you measures spin down in a parallel universe. All possibilities are realized, we just see one branch. A pilot wave theory, de Broglie-Bohm, reintroduces determinism. Particles have definite positions guided by a pilot wave. The randomness is apparent, not fundamental, arising from our inability to know the pilot wave's details. Objective collapse theories suggest wave functions spontaneously collapse when systems reach certain sizes or masses. Measurement isn't special. Collapse just happens naturally for large systems. Relational quantum mechanics says quantum states are always relative to an observer. There's no absolute state, only states relative to different systems. What's in superposition for you might be definite for someone else. Cubism, quantum Bayesianism, treats quantum states as representing an agent's beliefs, not objective reality. Quantum mechanics is about managing expectations, yet not describing what exists independently of observers. All these interpretations and others reproduce the same experimental predictions. They agree on what you'll observe. They disagree on what that observation means, what's really happening, what exists when nobody's looking. This might seem frustrating. How can we have such a successful theory and still not know what it means? But perhaps it's appropriate. Perhaps quantum mechanics is teaching us that the map is not the territory, that our mathematical descriptions, however accurate, don't exhaust reality, that there's always a gap between our models and what they model, between our equations and what they describe. Or perhaps the interpretation question is showing us that what's really happening might not have an answer. Perhaps at the quantum level, there isn't a single objective reality waiting to be described. Perhaps reality is more context-dependent, more relational, more dependent on what questions you ask and how you interact with it. After all, quantum mechanics works. It predicts correctly. It enables technology. It explains phenomena. Maybe that's enough. Maybe demanding a clear picture of what's really there is asking for something the universe doesn't provide. A classical style narrative that quantum systems simply don't have. The debate continues. Physicists and philosophers argue, write papers, propose new interpretations. And the beautiful thing is, quantum mechanics doesn't care. It keeps working regardless of how we interpret it. Particles keep behaving quantum mechanically whether we think they're in superposition, or splitting into parallel worlds, or being guided by pilot waves. Perhaps that's the deepest lesson of quantum mechanics. Reality operates according to its own rules, indifferent to our understanding. We can describe it mathematically, predict its behavior, harness it technologically, all without fully comprehending what it is. And maybe that's okay. Maybe partial understanding is the best we can hope for. Maybe the universe is under no obligation to be fully transparent to creatures who evolved to hunt and gather, not to understand quantum fields. So we keep exploring, keep questioning, keep pushing at the boundaries of knowledge, and the quantum world keeps its secrets, revealing just enough to tantalize us, to keep us curious, to ensure there's always another question waiting beyond each answer. And so we've travelled through 50 quantum facts, from the basics of wave-particle duality to the deepest unsolved mysteries of quantum gravity and interpretation. We've seen that reality at its smallest scales is stranger than our ancestors imagined, richer than classical physics suggested, more mysterious than any final theory has yet explained. Quantum mechanics reveals a universe that's fundamentally uncertain, yet precisely predictable, deeply interconnected yet respecting causality, built on probability yet creating stable structures. It's a cosmos where particles can be waves, where empty space seethes with activity, where observation participates in creating reality, where the future remains genuinely open. And perhaps most beautiful of all, this strange counterintuitive quantum world is the foundation of everything familiar. The solidity of matter, the colours you see, the light illuminating your room, the devices you use, the atoms in your body, all of it emerges from quantum rules operating silently at scales too small to see. You are, quite literally, a quantum system. A complex, warm, large quantum system where individual quantum fluctuations average out into classical behaviour, but quantum nonetheless. Your existence depends on electrons refusing to occupy the same states, on quantum tunnelling in the sun, on the Higgs field giving particles mass, on countless quantum processes operating seamlessly to sustain the classical world you experience. Perhaps there's comfort in that. You're not separate from the quantum strangeness we've explored. You're part of it, built from it, sustained by it. The universe's deepest layer of reality isn't something distant or alien. It's what you're made of, what you're woven from, what hums quietly beneath every moment of your existence. So rest now. Let these quantum thoughts settle gently in your mind. The universe will continue its quantum business. Particles tunneling, wave functions evolving, virtual particles flickering, fields vibrating, all without requiring your conscious attention. Reality is taking care of itself, moment by moment, measurement by measurement, creating the classical world from quantum foundations. And tomorrow, when you wake, the quantum world will still be there, still operating, still mysterious, still inviting deeper understanding, but for now, let it all go. Drift into sleep knowing that you've glimpsed something profound, the strange and beautiful architecture of reality, operating at scales too small to see but too fundamental to ignore. Sweet dreams, night traveller. May your rest be deep, your sleep be gentle, and your morning bring renewed wonder at the quantum cosmos we call home.